unmuting the microphone, but I guess it does happen. So we're going to talk about electrical basics today. We're going to start off with definitions. And the first one is going to be conductors. All right, conductors is going to be anything that's going to allow electricity to flow. So basically any type of metals, any dirty water, human beings, we're all conductors. All right, the most common conductors we're going to see in residential construction is going to be the wiring that we use. It's also going to be plumbing pipes as well, because when we talk about grounding and why we ground and how we ground, excuse me, that's all going to come into play there. So the most common ones we're going to run into in residential electric is going to be copper, pretty much. Other ones that we will see doing an inspection is going to be the aluminum, and then sometimes we'll run into some tin as well. All right. I'd like to address a little bit about these. So aluminum and tin, a lot of people get confused between the two of them. Now, they're both going to be silverish in color when it comes to, looking at the actual metal portion of it. Aluminum will be a little bit shinier and newer, and I know I have a picture of it here when we get later on into the slides. But the biggest detail and the easiest way to tell the difference is going to be that aluminum is always going to have the plastic insulation. When we're dealing with branch circuit wiring, I'm not aware of any aluminum wire that was made with the cloth jacket on it. Everything that was made with the cloth jacketed material, that was going to be tin. Now, when I say tin, that was actually copper. What we're talking about is tin cladding. So it's going to be tin cladded copper is what we're going to refer to it as. Aluminum in residential wiring, that was used around the mid-60s to the mid-70s. If you don't know that already, you are going to want to write that down. So again, it's the mid-60s to the mid-70s. It's going to have plastic insulation, and single strand wiring really isn't allowed anymore. So the reason is there was something called aluminum creep. When it got warm, the aluminum wire would expand, and then when it cooled off, it would shrink. So the more it got used, the bigger it got, and the smaller it got. That actually loosened up a lot of wires, or a lot of the screws that held the wires together. So because of which, there were fires that happened in homes, and the fire investigations during their cause and origin have determined that it was because of the aluminum wiring that was in the house. They brought that to Underwriters Laboratory and a few other places where they did the testing, and then they started making changes into not allowing single-stranded aluminum or solid aluminum to be installed in any sort of houses. Now, here in the state of Illinois, it should be known that we do have mandatory defects that we have to report to our clients. One of those, and there's only 5 of them, but one of those 5 is solid aluminum branch circuits. All right. So let's talk about that a little bit. The difference between solid and stranded is, to me it's kind of simple. It's if it's one solid piece of wire that's coming in there, or a single strand of wire that's coming in there, then it's a solid wire. If there's a whole bunch of strands that are in the wire and they're twisted together and then that's covered with the plastic insulation, that's stranded wire. All right. The difference between a feeder wire and a branch circuit, feeder wires are going to be coming from either the pole to the panel. They'll go from a panel to another panel. Those are feeder wires. Those, by definition, can actually be solid aluminum, but because of the flow of electricity, I don't think I've ever seen that much. We just can't get that much electrical flow that we're going to need in a house for those connections in a single strand. So solid aluminum, we talked about if it has the plastic insulation. Solid as opposed to stranded, and branch as opposed to feeder. You should be able to identify those. So when we talk about the flow of electricity on these things, there's another term I'd like you to be aware of called skin effect. Now, it's not a foolproof 100% deal, but it's still a good way to think about it. When we talk about water flowing in pipes, water flows inside the pipe. When we talk about electricity flowing on wires, they actually flow on the outside of the wire. So they flow on the skin. So knowing that term skin effect says that if I have one wire, then it's only the surface area of that wire where the electricity is going to flow. If I have a stranded wire, I have a whole bunch of surface areas, and that's going to allow electricity to flow easier. A nice analogy I like to use is the difference between melting ice. If I have 100 pounds of crushed ice, that's going to melt faster than 100 pounds of a solid block of ice. Because again, ice melts on the surface. So if there's more surface area with the crushed ice, then that's going to melt faster than the block of ice. Same thing. Electricity is going to flow easier on stranded wire than it is going to be flowing on solid wire, and that's because of the skin effect. So the speed of everything, in the conductors, the easiest flow of electricity, I think, is the tin. Right behind it, almost 100% of it, is going to be the copper. So they're going to be nose to nose, and tin would go just a little bit faster. And the last one is going to end up being aluminum. I kind of like to refer to that as the horse race, and that's going to end up being beetle bomb, and it coming in at last. So what does that mean? Some of what we have to do, I'm going to zoom in on that board a little bit, sorry. Okay. Some of what we do is check wire sizes and make sure we have the right size breakers that protect these things. So I know in the NEC they have a pretty extensive layout on what size wires, what size breakers, the distance that comes into play, the temperatures that come into play. But for the most part, for us, it's pretty standard. All right. So I like to encourage people to make a chart. And the first thing we should be doing is 3 different columns. The first column is going to be amps, and then we're going to put up here copper, and then aluminum. Okay. And now the amps are going to be pretty much our breaker sizes when we deal with this. So the most common breakers we're going to run into are 15, 20, 30. We're going to jump up to 50, 60, 100, and 200. So then if we draw a line coming across with these, we'll be able to write down what size gauge wire, or bigger, what size gauge wire should be on these breakers, all right? So if I had a 15 amp breaker, I should expect to see a 14 gauge wire if it was copper. I should also expect to see a 12 gauge wire if it was aluminum. Remember, we said electricity has a little less, it flows slower on the aluminum than what it does on the copper, so we're going to need a bigger wire, more surface area to allow that electricity to flow. 20 amps, 12, aluminum 10, copper 30 amps is going to be 10, and then this is going to be 8, 50 amps is going to be 8, and then 6. Hopefully you're seeing a little bit of a pattern here, as we go down into the wire size. 60 amps is 60, aluminum is going to be a 4, and 100 amps copper is a 4, but I like to put that off to the side. In the Chicagoland area, we're actually going to normally see a 3. So and it's not going to be in any tests or anything like that, but if you're going to operate in the Chicagoland area, I'd like you to know number 3 and Chicago. Number 2, aluminum. This is one of our more common feeder wires that we're going to see in residential electricity when we deal with the 100 amp services. And the last one, we don't follow this scale. We kind of flip it around a little bit. We go 2 and 4. And then what we're going to do is put a /0 after the end of that. And that /0, the 0 stands for aught. So it's, if it's 1 0, it's 1 aught, 2 aught, 3 aught, 4 aught. Once we get bigger than 4 aught, then you start getting into MCM and just bigger electricity that we're not going to deal with. All right. So another term is cladding that's up there. All right. And cladding is basically when we put an object around another object. In other words, if I have vinyl cladded windows, that means I'm putting vinyl wrapped around a wood window. All right. So we actually run into stuff like tin clad copper, which I had up on the screen before. That means the actual wire itself is copper, but it's got a coating of tin on the outside. And since most of the electricity, if not all of the electricity, is going to flow on that tin, that's what we're going to be measuring as the wire and the wire gauges that we're going to be using. One that's kind of unusual is something called copper cladded aluminum. And I shouldn't say that it's unusual. It's a very common wire that we run into. And quite frankly, I don't think anybody's going to really recognize it unless they cut the end of the wire and peek up in there, or they're able to read the writing that's on the insulation itself. All right. But in this case, we have a aluminum wire that's cladded with copper as it comes in there. So I always like to ask a little bit of a test question whenever I'm doing these classes, and I know we really can't answer them right here, so I'm going to end up giving you the answer. If I had a 10, or let's say 100 feet wire, 2 of them, one of them was a solid copper wire, and we're going to say it's a 14 gauge solid copper wire, 100 feet long, and then right next to it I had another 100 foot long copper cladded aluminum wire, same size, they're both 14 gauge, they're both the same distance, they both have 120 volts pushing the electricity to them, they have the same amount of draw at the other end. So I always try to ask the question, which one is the electricity going to travel the fastest on? Is it going to be the copper cladded aluminum, or is it going to be the solid copper wire? And I usually get a mix of both, but if you take into account that skin effect, they're both going to be the same, or at least they should be the same when we come with it. This chart up here, I'd like to encourage you to write it down and memorize it. Every home inspection that we do, we're going to look at the breakers, we're going to match them up with the wire sizes, and make sure we have the right size breaker. Many times we're going to see things that are over fused. It's common. All right, so if I got a 14 gauge wire on a 20 amp breaker, it's not designed to carry that. Let's see if I could switch these lights a little bit. It's not designed to carry that as much. And when that happens, that's considered overfusing. Now, in all reality, and I know I'm recording this, so I guess I can't deny it, I really don't see that as a big deal if I got a 14 gauge wire on a 20 amp circuit. It's wrong. I'm going to identify it as being wrong. We're going to document it. But, fixing that is just put the right size breaker in there. And most of them aren't that expensive, so we're not going to get too much into it. But if I got a 14 gauge wire on a 40 or 50 amp breaker, now I'm really rolling the dice. That breaker is going to allow 50 amps to travel through something that's really only designed to carry 15 amps. And then I'm taking a big push on it. So every inspection that we do want to check and make sure that we do have the right size breakers for the right size wires. Now the other way around really doesn't matter. So if I had a 10 gauge wire on a 15 amp breaker, I don't care. I'm just limiting the flow that's going to go through there, but it's not like I'm creating any sort of hazards. I'm not making the wire the weak link, and that's what we want to avoid. We don't want the wire to end up being the weak link. All right. Insulators, and I guess I should take into account other conductors. We have a lot of lead service feeds in this area, so lead is a conductor, and we use that for our grounding electrode conductors, our connections to those. All right. So insulators, the most common one we're going to have is going to be plastic. Pretty much all copper is going to end up being plastic insulation. The second one is going to be cloth, and that's going to be our key identifier to find that tin clad copper wire. Those are going to be in the older homes, usually pre-World War II, so stuff before the 50s, but you might still run into it in houses afterwards. That doesn't mean it's going to be the end of the world. All right. Next word I want to work on is grounding. Grounding, I like short, simple definitions. So anytime we connect anything to the earth, we have grounded that item. All right. In Europe, they actually call it earthing. Here in the United States, we call it grounding. Not only do I want you to know what it is, but I want you to know why we do it. All right. Now, there's a couple other reasons, but the two main ones that I want you to remember is to maintain zero potential. The earth has electricity in it. All right. If you think about it, it's nothing more than a gigantic electromagnetic generator. So we do have a metal core that keeps spinning, and it does create electricity. With that, we have a north pole and we have a south pole. And if I had a compass, that electromagnetic field that it would be created, that compass would be pointing to the north. All right. Now that voltage, that electricity that's in the earth that's being generated, that varies. That goes up and down. It changes. All right. And when we talk about voltage and electrical flow in a little bit, we're going to be discussing how I have to have a different voltage for electricity to move. If they're both the same, then electricity is not going to move. Plain and simple. So as it fluctuates, and another analogy, I guess I should back up, I like to use is sea level, because we can actually see that with our eyes. Sea level is always going to be known as zero, but anybody who's ever been to the ocean knows that every day, twice a day, the sea level goes up and the sea level goes down. It changes, it fluctuates, all right? But no matter where it is, we're always going to call sea level zero, all right? The same thing with our electricity, our static electricity, our voltage in the earth. We're going to call that zero, no matter if it's gone up or down. Now, the goal is to attach everything to the earth. So as the earth changes, then the items changes. And as long as everything's the same, then electricity is not going to flow. Where the problem comes into play is if the electricity changes and this object doesn't, we as humans come in between there. It's going to want to equal out. Anytime there's a difference in voltage, we're going to touch it, and there's going to be a shock or a zap that ends up coming to it. The next thing I want to talk about is lightning protection. And I guess I'm going to back up on the grounding as well. I hear a lot of comments where people say that, well, that's where all the extra electricity is supposed to go. We want to give it a path for the extra electricity to flow into the earth. Okay? We do not want to let any electricity that we generate and we pay for, we do not want to let that electricity flow into the earth. We don't want to waste it by sending it down there. It's wasting our bill. In fact, that's called a fault, more specifically a ground fault. Anytime electricity goes someplace that it's not supposed to go to is considered a fault. And if it goes into the earth, we call those ground faults. All right. And I usually pop up another example, like I'll take a wire and I'll pretend that we're going to put this into the energized slot of an outlet. And let's say it's a 15 amp outlet. And then I'll take the other end and I'll go outside and I'll have a ground rod out there all by itself in the middle of the yard, driven into the earth, a good 10 feet in there. So I have a good electrical connection to the earth, and I attach the other end to that ground rod. So I got a 15 amp breaker on a 120 volt circuit with a 14 gauge wire, and I have it plugged into the energized slot of an outlet only and to the ground rod outside. All right. Now the earth is going to be 0. That energized slot of the conductor is going to be 120 volts. They are going to be different. So anytime I have a difference in voltage, electricity will flow. All right. But the earth is also a big resistor. Resistors limit the amount of electricity that's going to flow. Now, there is an ohm test and everything else. I'm not going to get into that because, quite frankly, I think it just complicates things too much. At 120 volts pressure, it's easier for me to remember that somewhere around 5 amps will be flowing into that earth. So electricity is going to flow. It's going to flow into the earth. It's going to be about 5 amps. And I'm going to be on a 15 amp breaker. So that 15 amp breaker is just going to see 5 amps of electricity flowing. As long as it only sees 5 amps of electricity flowing, it doesn't know that there's a problem. It just lets it flow. It's not going to turn off until I try to flow more than 15 amps. That's when the breaker is going to trip. But all that stuff is still energized. It still has potentially more electricity. If anybody touched that and they touch another pathway, then they're going to also become a conductor, and that's why that's dangerous. Anytime we have electricity going someplace that it's not supposed to go, we want that power turned off as soon as possible. All right? We don't want it to stay on. We don't want to let that extra electricity go someplace. The only thing we're trying to do with that grounded connection is keep that 0 potential. Keep everything in the house at the same potential so that anything that I touch inside after I've been outside will always be 0 or whatever the earth is. And I won't be getting any shocks when I touch anything. Now, the other reason is going to be for lightning protection. Obviously, lightning is going to have a lot more than 120 volts of pressure. It's going to, I really don't even know what it is. It's a tremendous amount of pressure. Creates a spark from the sky all the way down to the earth. If that ends up hitting the house, then we need to give that electricity a place to go. Otherwise, it's going to find any path available. So we want to let it go into the earth where it could safely disperse, and then it's gone. But a lightning strike is just a split-second moment of time. And we're given that particular electricity a very specific path to get into the earth and not damage anything in the house. So going back, grounding, the short, simple definition is item to earth. All right? Any item. I don't care if it's a deck, a porch chair, or my electrical system, which we'll do in most homes. All right. Anytime we connect anything to the earth, we have grounded that particular item. All right. Why do we do it? To maintain 0 potential and in case the house gets struck by lightning. Next term is bonding. And forgive me for not editing that one. I slipped on it. It's item to item is what I want you to remember, not item to earth. Obviously, I copied and I didn't edit that one slide. So item to item. Any 2 different items. So if I have a hot water pipe and a cold water pipe, all right, and then I make a connection between those 2 pipes, I bonded those 2 pipes. The reason we bond them is so they maintain the same potential. The reason why I want the same potential is because if I grab one with one hand and then I grab the other with the other hand, I end up becoming the conductor, and I will equal those out. We don't want that to happen. We want to make sure that those 2 items are going to be the same potential so that if somebody grabs those 2 items with both of their hands, then they're not going to be the conductor that's going to equalize those things out. All right? And if you think about it, so maybe it's not such a bad thing if I have item to earth up there. The earth is an item. So anytime we take our house system here in the house, we're really taking our grounding system of our house and we're bonding it to the earth. So really the only difference is when I use earth as one of those bonding items, instead of saying bonding, we're going to call it grounding. All right? And that 0 potential, well, we're going to say whatever the earth is going to be the same potential. So we want all those objects to be the same. All right. But same thing, especially around pools, when people get out of the water and they're touching, the water in the conduit or the gunite and the metal inside the pool, that's going to be whatever the earth is. If I get out of that and I touch the ladders and the diving board, all those have to be bonded together because, again, I don't want to be the conductor that's going to equalize or equal those items out. So review real short, conductors, anything that flows electricity. So typically in our homes, it's going to be aluminum, copper, and tin. Insulators, anything that stops the flow of electricity. So when I have an energized wire and I touch that wire on the plastic, I don't feel the shock. As long as that plastic insulation is as strong as it's supposed to be and it's not damaged, I'm not going to feel a shock. Right? That's my insulator. That's going to stop the flow of electricity. It's going to keep it on the conductor. Grounding, item to earth. We do it because we want to maintain zero potential. The earth is the biggest item on the earth because it's the planet, and nothing can be bigger than the planet on the planet. So that's going to be our reference point that we're going to use, and we're going to call it 0. And also lightning protection, we need to give that a pathway to get to the earth. Bonding, item to item. Why do we bond to maintain the same potential between two objects? All right. All right. Next word we have up here is amps. I like one-word definitions again. And for amps, I'd like you to know that is current. All right. The biggest thing about amps is they don't disappear. We can cancel them out, but they don't disappear. In other words, if I have a light bulb on a circuit, and let's say it's a 120 watt light bulb, if I have 120 volts and I want to use 120 watts, then I'm going to use 1 amp of electricity to allow that 120 watts to flow. Amps don't disappear. So if I have 1 amp going out on the energized conductor, then I'm going to have 1 amp coming back on the neutral conductor. Watts is the power. I like to remember the term power with watts because we pay for power. It's just easier for me. The P's together, make it simple. So power, watts, they travel at the speed of light. So the generator of the earth that's coming in here, that's going to go ahead and create the wattage, create the power. It flows through my panel, through my breaker, through my wires, goes through the light switch, goes to the lights that are lighting up, and then it changes to either light or light and heat. It changes to whatever that object is, and then it's gone. All right. So we pay for whatever wattage we use that's going to be creating those lights and doing whatever it needs to do. All right. So wattage travels at the speed of light, and it stops when it gets done doing the work that it needs to be doing. Volts is pressure. I like to think of it as a magnet. In fact, when we create electricity, we're taking coils and we're sending them around a magnet to go ahead and produce that voltage or that magnetic pull and push where it comes to it. So the volts and the pressure, the difference is going to be whatever the difference between the two objects is. Anytime I do have a difference, that's going to be causing an electrical flow. They're always going to attempt to equalize out. But if I keep adding more wattage and more voltage to one side, then it's going to keep flowing and flowing across as it comes to it. So in that analogy that I used before, where I had the wire on the energized conductor side of the outlet, that was at 120 volts of pressure. We know the earth is going to be 0, so I had a difference of 120 volts, or at least somewhere in that ballpark. And because there's a difference, electricity is going to constantly flow. Now, if I keep adding electricity, it's going to keep on flowing until it's equalized out. All right? Ohms, I want you to remember it as resistance. I used an analogy of a light bulb earlier. That thin filament, if we go back to those old incandescent light bulbs, that thin filament actually limited the amount of electricity that would flow. That was the resistance. That resistance limited the amps, limited the wattage. It doesn't limit the voltage. The pressure's still there. It's just how many watts and amps are going to be flowing through it. So if that wire is thin enough where it only allows 120 watts of electricity to flow, and I have 120 volts of pressure, that's how I come up with my 1 amp. We divide the watts into the volts, and that gives us the amps where it comes to it. So ohms is resistance. It limits the flow of electricity. And going back to our grounding example before, I think I said 5 amps. It's partly because that the earth is a gigantic resistor, all right, for lack of a better term. And that, so when electricity flows into the earth, it's really trying to get to the transformers on the pole. But that earth is creating a resistance, ohms, and it's limiting the amount of flow that's going through it. So as long as it keeps limiting that flow, we're not going to exceed the breaker usage. We're still going to stick in that 5, 6 ohm range, somewhere in that ballpark. All right. Okay, sorry about that, and I'm going to have to, for some reason I ended up with a crash on the computer. All right. Okay. Alrighty, well, looks like we're getting it back up and running again. Alright, so forgive me for not knowing your name and who this is, but somebody said it's too many amps. So I'm going to assume that what you mean by the amps that's flowing into the earth, you think it's going to be less than the actual 5 amps that I was saying it is. And it may be. And we're not going to put an amp meter on it to find out exactly what it is. There is a mathematical calculation. The biggest point I want to get out of all this is going to be that it's not going to be enough to cause the breaker to trip. And that's the bottom line. So the next thing I want to talk about is phases and identifying voltage and how we do it. I meant the PC crash, too many amps, got it. All right. It probably is the case, you know, but it's an Apple product and these aren't supposed to be doing that. But we'll see what happens later on. But anyway, when we determine the voltage in a house, we mostly just basically look at the wires. We don't put voltmeters on there and determine what it's going to be. So we're going to, if we have 3 wires that come in there, well, let's start off with 2 wires. If I have 2 wires that come in there, we're going to assume the first wire is going to be the neutral conductor or the grounded conductor, and then the second wire is going to be an energized conductor. So if I have the neutral or grounded, that's going to be my 0, and if I have an energized conductor, that's going to be my 120. Now I really don't care if you say 110, 115, 120, none of that really means anything to me. Because again, we're not going to get the exact voltage that comes in there. What I do care is when we get to a single phase with 2 energized conductors that we use the proper terms. So if I have 3 wires coming in, the first wire is going to be the neutral wire again. Then I'm going to have 2 energized conductors. That 2 energized conductors then is going to be a combination system, and we're going to refer to it as either 110 220, 115 230, 120 240, whatever it is. Whatever you use on that first number, all I'm asking is that you double it. It's going to discredit yourself real quick and easy if you try to say that it's 110 240 or something like that. So just using the right terms is always best. And if we look at the picture in the diagram that's coming in there, the middle wire of those 3 wires, that's my neutral. That's my 0, all right, that comes in there. So if we take the energized conductor on the left-hand side, that's going to be at 120 volts. If I measure the difference between the neutral and that 120, or neutral and that energized conductor, I'm going to get that 120 volts. If I measure the same thing on the right side, energized conductor, and I measure that between the neutral and the energized conductor, that's still going to be 120 volts. And then when I measure between the 2 energized conductors, and this is where I get the 240 volts, that's going to go ahead and measure out. One will be positive 120, and with alternating current, it's always going to change from positive 120 to negative 120. Positive 120, negative 120. And when I show the sine wave a little bit later, because we are going to go over this a couple different times, when I show the sine wave a little bit later, you're going to see how it goes positive, negative, and it actually does that about 60 times every second, all right, and which we call a 60-second cycle, all right. So when one wire is positive, then the other wire is going to be negative, and then in between the 2 of them, that's going to be 240 volts of pressure that comes in there. One thing that I get asked a lot. Now, this breaker just has 1 switch on it. But sometimes we'll see a 2-pole breaker. And if you look at the 240 circuit on the left side, it looks like it's on the right side as well. But either one of those, we're going to have a bar that ties the 2 of those together. And let's say each one of those is 30 amps on each one of those switches or breakers. And what we don't do is we don't add them up. All right, so if it's 30 and 30, that doesn't mean that it's a 60 amp circuit. All right, same thing with our main disconnect. We don't add up however many amps are going to be flowing on there. So it's hard for me to see on this one. I'm going to guess that's, I'm just going to guess it's 100 amps, and it doesn't matter what it is. We're just going to make an assumption to that. So if it's a 100 amp circuit that comes up there, that means I'm going to allow up to 100 amps to flow on my energized conductor. I'm going to allow 100 amps to flow on the other energized conductor. And if you remember, I said amps don't disappear. So, off the cuff, I could start thinking, well, shouldn't I be sending 200 amps if they're fully loaded up there? That's not true, all right? They don't disappear, but they do cancel each other out. And that's why we can get by with 2 energized conductors and only 1 neutral. We don't have to have 2 neutrals coming back out of it. In fact, nowadays we do what we call shared neutrals on many circuits inside of a house. All right. So if I had 100 amps flowing on the right side energized conductor, and I had 0 amps flowing on the left side conductor, I will have 100 amps flowing on my neutral conductor. Since all 3 of these wires are designed to carry 100 amps, not a problem. So let's take another scenario, kind of the same. 100 amps flowing on the right side conductor and 100 amps flowing on the left side conductor. All right. That's going to, since one is positive and the other one's negative, positive 100 plus a negative 100 actually equals 0. So if they're both the same, I will not have any electricity flowing on the neutral. There's going to be some situations, such like central air conditioning heat, well pumps, electric radiant baseboard heat. Those objects, everything that's in those appliances are all 240 appliances, because of which both phases are going to be equal. You're going to see that they don't even run a neutral wire to those items because we don't need it. We only need the neutral wire in case those two energized conductors are different. So if I'm flowing 100 amps on the right side and I'm only flowing 50 amps on the left side, that means I'm still going to have 50 amps that's going down the neutral. I have to bring that imbalance back. The first 50 will cancel each other out, and then whatever's left over will go down the neutral. So the only way that I can even get up to 100 amps is if I have 100 amps flowing on one side, 0 on the other, and that's going to allow me to have 100 amps flowing on the neutral wire. Then as soon as I start adding electricity to the left side or amperage to the left side, that brings down the neutral. They're going to cancel each other out. So, and I mentioned before about appliances such as well pumps and central air conditioning systems and electric radiant baseboard heat. Those don't require a neutral system. But let's say I hit an electric stove or electric dryer. All right, those are also 240 appliances. But with those appliances, I actually need a neutral wire. And the reason is because I'm going to end up having 120 light bulbs in there, maybe a 120 computer. So that's only going to take power off of one side. It's not going to be equal on both sides. Because it's not going to be equal on both sides, now I have to have a neutral bringing down the difference. So we're going to end up with 2 energized conductors, 1 neutral conductors, and we should have also a grounding just in case we get a phase fault or something happening there. All right. Okay, so identifying the amperage, there's a few different things that we have to look for when we're doing that. Number one is going to be the main breaker. All right, now it does happen that somebody can go in there and replace a panel and they'll use the old wires that were in existence then, and then they're going to put it on a 100 amp breaker, and then all of a sudden they're going to be advertising that we have a 100 amp service, and yet we still have a number 6 copper wire that's feeding the system, and that number 6 copper wire is only designed for 60 amps. But yet now I have a 100 amp breaker on it. That doesn't make it a 100 amp service. So there's a few things that we need to look for. I did post this chart up on my website, thehomeInspectors.com. Sorry for the cheap plug. But if you go to education and employment on there, you're going to see where determining the amperage chart is up there. So stuff that you're going to need to know is size of the main breaker, size of the service entrance cable, so the wires that are feeding us. And we go back to the chart that I wrote up earlier. You're going to need to know the rating of the disconnect panel. So that's this panel here. You're going to need to know the rating of the meter panel itself, which is going to be on the outside. Now the problem with the meter panels, we don't have access to the inside to see the data plate. The disconnect panel we do. So sometimes it'll be on the back door or on the dead front plate. Sometimes it'll be either on the left or the right on those things, but we do have access to them, when we're looking at this stuff. So we can see what the chart and see what they're rated for. And then we want to go whatever the weakest link out of those items are. If that main disconnect that we're looking at here is not equal to or less than everything else, then it's considered dangerous. All right, that means we're going to allow more electricity to flow through one of those items that the electricity isn't designed to carry that much. All right, another item I left off the list is going to be our service entrance pipe and the size of that cable coming in there. I can't put too thick of wires inside of that either. So whatever our weakest link is, that's what we're going to be pointing out. So this is where we're talking about our meter enclosures. Let's see if I could do something here. Nope, I can't. All right. I'm just going to have to fix this on every slide until I figure out why the problem is, and I'm not going to solve that now. All right. All right, so meter enclosures, I'll show you a picture of those in a little bit. And in fact, let's just get right to these things. The pipe sizes, if you want to write those down, that's going to be on the chart on my website. So 3/4 inch to 1 inch is roughly about the 60 amp mark. 1 inch to 1.5 inches is going to be the 100 amps, and then once we get to 2 inches and above is where we're going to start getting to the 2-inch marks coming in there. Oh, I think I figured out here what's going on. Maybe I haven't. Okay. Okay. So as we get it back into the meter enclosures, we talk about the different shapes, and we're just going to zip right through these and go back to the meter enclosures that we're seeing. All right. So these typical square boxes, they call A boxes. The panels, now we're not talking about the meters themselves, we're talking about the actual panel. Those are usually designed to carry somewhere around 60 to 100 amps. You're going to see these with a lot of number 2 aluminum wire service feeds coming in there. So 100 amps is pretty typical in our area. All right. These old rectangular ones with the glass in there, these again were typically 60 amps that came in there. And without getting inside of it, we're not going to know. But yeah, if you start seeing 100 amp services on these things, that means somebody changed the panel and the wires coming in there. I don't think it's necessarily the end of the world, but when, you know, a problem is never a problem until it becomes a problem. And if these things are only rated for 60 amps and we're seeing 100 amp service coming in there, we should be calling these things out. Again, just another view, the rectangular ones with the glass front in here, these are typically for 100 amps. This one I like. It's an old round meter panel. If you had a test on this one, I would be calling it as 30 amps. You will see up to 60 amps into these systems. Sometimes they do let them be overfused in a little bit of a way, but 30 amps is going to be the magic number I want you to remember. This one is our most common one that we're going to run into. And these are typically for 100 amps. I have seen them gone up to 200 amps. But mostly the meter panel ratings for these things are going to be at 100 amps. The bigger ones, the larger rectangular ones that go into the earth, these are going to end up being for 200 amp services. They're just more common. Again, 200 amps underground coming in here. You can see how much wider the panel is and how much more area it's able to hold. All right. Let's move here. Older service meters, and we don't really see too many of these things where they say 15 on them. Those are typically going to be for up to 100 amps. This 130 is up to 200 amps. These are the old one-way meters. Everybody's switching over to the smart meters now. We just don't have these dials or clocks on there any longer, all right? You know, here's another one, CL, another old dial meter, one way. You know, sorry I don't have a picture of the newer one. I thought that was up in there. All right. Wire gauge is going to be our next thing. We went through it before. So typically we're going to either see a number 6 feeder coming in there. That's going to be for 60 amps. A number 2 aluminum or a number 3 copper. And these do need to be committed to memory. Those are what we're going to see for 100 amps. And then we're going to be dealing with 2-aught copper, most likely for 200 amps where it comes into it. And that's what they're showing here. So I know it says number 4. That is what the NEC calls for. But very common in the Chicagoland area, we're going to see number 3 coppers. Wires at the service mass need to be the same as what's in the panel. We run into this quite a bit. You're going to see that the mass that comes down there all of a sudden might be a number 6 wire, or even the service drop coming across the top could be a number 6 wire. And then as it comes inside, it's either bigger or smaller. So somebody got into the meter and changed things out. We want to make sure those wires are the same size. And at least, you know, we should be suspicious when things are changed. I also like to look at that tag on the meter panel. And it's a tamper tag. If I see that that's cut or broken in any which way, then I know that somebody was in there doing some sort of work. In our area, the electric company is the authority having jurisdiction. They're the ones that can approve or disapprove any sort of hookup where it comes to it. So if they want to have smaller wires that are feeding their system, they could do whatever they want to do. You know, they're the authority having jurisdiction. But for me and for our company, we don't want to take ownership of issues. So if we see something that's out of the norm, we're going to document it, plain and simple. Meter panels are not supposed to have anything coming off of them. All right, so if we do see an outlet or something in here, we don't know if it's before the meter or after the meter, but either way, we're not supposed to be using the meter panel as a junction box. And so we can't run wires through it. So we shouldn't see any taps coming off of it either. This one I just thought was pretty cool. They could have advertised that free air conditioning was being given. So if you look at the meter in the upper right corner and we follow that pipe coming down, we see that it goes to the disconnect for the air conditioning. We go to our seal tight and that feeds there. Now if this was all done before the meter, that wattage that's being used for that air conditioner is not going through the meter. Hence that meter's not going to end up being reading any sort of electricity that's going to be done through the air conditioning unit. We do have to do a little bit of writing here. If we have an overhead service drop, then we need to know what our clearances are. So these do need to be memorized, all right? Roadways, 18 feet. I'm more worried about the NEC. ComEd is for my local jurisdiction. They do allow less, but we don't see too much of that, all right? So roadways, 18 feet. Residential driveway, 12 feet. I would like you to still know driveways that are designed for farm equipment, that's actually 15 feet. So 18 for roadways, 15 for farm equipment, 12 for residential driveways, pedestrian, or any place that I could walk underneath those wires, whether it's a deck, lawn, sidewalk, whatever, 10-foot clearance from that. Windows, doors, porches, etc., that's 3 feet, and that's mostly horizontal and below. All right, so as I measure that, that's going to be, if I'm standing in front of a window and I'm looking out, so we're going to go from the one side to the front, to the other side, to down below us. That's all 3 feet. 5 feet for the local electric company here in Chicago, but 3 feet for the NEC. That doesn't include above, all right? I could be right above the window. I can't be in front of the window, but I can actually be right above it when it comes to it. Other things that come into play is over roofs. Let's see if that's here. It is here. Good. When we're dealing with over roofs, if it's a sloped roof, And a sloped roof is anything over 212. All right. Anything under 212 is going to be considered a flat roof. We have two numbers that we have to memorize for this. It's 18 inches and 3 feet. And it all depends on the horizontal run. All right. So what we're saying in this drawing is that from that service mast till it gets to the overhang, that has to be less than 4 feet. If it's less than 4 feet, then I could be within 18 inches of the roof. And we're talking about the lowest point. So here we see that there's a splice that's pretty much our lowest point on there. Maybe it's right at the gutter line. But that lowest point has to be at least 18 inches off the ground. Now, if that horizontal run is greater than 4 feet, then that changes to be a 3-foot clearance to that roof line. These are our windows again. Again, 3 feet, right, left, front, below. And it's just the wires. We're not talking about the mast or the pipe that we see. We're talking about just the wires themselves. All right. So where that drip loop is coming into play, because that's less than 3 feet from that window, that's something we should be calling out for clearance issues. Clearance issues also come into play at the panel down in the basement. We need to have enough room to where the electrician or who's ever going to be working on this panel that they could work on it safely. All right. So there can't be anything that's going to trap them into this little area, and it needs to be wide enough so they could get in there and work. So if you're going to be memorizing numbers, 30 inches width, and it's not 30 inches from the center or from the left and the right, it's just 30 inches total of working room in front of it. So if this thing's off in a corner, kind of on one side, but I still have a good 30 inches or more workspace to it, that's okay. Behind the panel is 36 inches. If I have to crawl into a tub or I got a post or something that's supporting things, then that comes into play as well. The height of the panel is typically 6.5 inches. The area above the panel is kind of a safety zone for the electric. There really shouldn't be anything that goes up there above it. We want to let more conduit or anything that's going to expand on the system. We want to give them easy access. I mean, I don't have it in me to tell somebody to go ahead and move that waistline that's above it, but it would have to get me to start thinking. If I thought that it was put there originally, I would probably be less inclined to say something about it. If I thought that it was a rehab and it was added, then I think I'd be a little more inclined to say something about it. So again, no foreign objects are above that panel. It's a dedicated space. One thing that Corey put in here for me, which I'm thankful for, is he cited the actual codes in the NAC where it's in there. So if you want to verify this, that's where you would find it. The maximum height of the breaker is 6'7". Usually they're going to be around eye level is what I like to see. Common sense here. We got the electrical panel behind the water heater. There's really no way of anybody to get in there and do any sort of work. Stuff like that is kind of a no-brainer. All right. So this is a little bit of review of what we saw before. We're still going to refer to these as a single-phase system. Again, we're only going to be counting the wires that come in there. Now, this picture throws a little bit of a curveball because one of those wires that we're seeing is the grounding electrode conductor. And on the left side, there's a bus bar, and that's attached to the back of the panel. And that's where my grounding electrode conductor is attached to. All right, so we're not going to count that wire when it comes into it, but we are going to count the other three. Neutral, hot, hot. One of the other things, too, when you open up the door to the panel, if you see two breakers tied together, so a 240 breaker, then that's another good clue that you have a single-phase 120-240 system. If you open up that door and you see three breakers tied together, and this is going to be either on condo buildings or big, large homes, and those are three-phase systems. We're going to stay out of those. They can start creating arc blast that gets really dangerous. It's going to be over all of our heads. I'm going to ask that you refer them off to an electrician and just say you don't know. So don't take the cover panels off unless you know what you're doing on those. Again, you're going to have 3 energized conductors. The easiest, quickest clue that you're going to end up seeing those are going to be 3 breakers all tied together when it comes to it. So typically, again, they're going to be on either commercial buildings or very large residential buildings that comes to it. So we mentioned before about measuring between the hot and the neutral, 120. We measure between the hot and the hot. That's where we get our 240 comes in there. So this is our typical sine wave. And the way this works is I'm going to have a magnet that's going to take a coil. One side of the magnet will be positive, the other side of the magnet will be negative. And each time that goes around, that coil is going to create a positive charge, a negative charge, positive charge, negative charge. In which case it's going to create positive voltage, negative voltage. And that's going to happen 60 times every second that it's going to revolve around there. Hence we get the 60-second cycle. Now with a 120, and that was a 120 sine wave that came in there. That was one cycle that you saw. When we're dealing with a 240 cycle, it's basically the same thing, but both of those wires are completely out of phase of each other. So in this case, the blue wire would be the same one we saw before, where the red wire would be the opposite as it comes in there. But you can see when one is positive 120, the other one's negative 120, and then they switch places. The difference between the two of them, maxed out, is going to be 240 volts. Now the electrical panel, talk about clearances, and these are meant to be a little bit humorous, but you're going to run into them. When people finish their basements, if they want to have a bathroom or a shower and that electrical panel is there, then I guess they're going to put the panel in shower and everything right where the panel is. I mean, it doesn't take a rocket scientist here to determine that that's just not a smart move, all right? And granted, we don't want to let any water get in there. That's true. But more realistic, I mean, just putting the plastic over it isn't really going to protect anything. It's the humidity. So if that humidity starts getting into that panel, that humidity causes things to rust. Rust is resistance. Resistance creates heat. And that's when we start getting into problems with our electrical panel. All right. So here we lifted it up. It's just not a smart idea. I do want to show you what aluminum wire looks like, more specifically solid aluminum. These are the neutral conductors that are coming back, and they're on the neutral bus bar. But you can see that we have plastic insulation. You can see how silver and shiny everything looks in these diagrams or these pictures. And again, this is a mandatory defect. Solid aluminum branch circuits, we do have to report the presence of that. And that's per the state of Illinois SOP. CUAL, COALR, those are all different ways to determine whether or not the appliance or the breaker or the switch or the outlet is able to take copper or aluminum or both. All right. And so if you see COCU, that stands for copper. AL, ALR, that stands for aluminum. If you start seeing a do not enter sign on these things, then that's going to be a problem. So this slide here talks again about the solid aluminum branch circuit. All right, so if it's stranded, it's okay. If it's a service wire or feeder wire, that's okay. Doorbell, other transformers, those are typically stranded. That's going to be okay. Aluminum wire will be in plastic and not in cloth. Even though I still think tin clad copper is just ridiculously old and it gets dried out and brittle, that's just my opinion on it. It's not a mandatory defect. So we don't have to call that out. That's going to be focused more on your opinion. I mentioned earlier when we were writing some things down that solid aluminum branch circuit was used from the mid-60s to the mid-70s. The aluminum wire industry is actually making a push to put their wires back into residential electric. Their solid wires back in here. They say that they've remixed the aluminum and redid it so it doesn't have that aluminum creep and that different sizing stuff that comes in there. And they feel that it's safer. They're still requiring that things have to be torqued because obviously they don't want to take responsibility to stuff. And because nobody's ever going to be torquing and tightening screws and wires. So far, The code officials are just fighting it, and they're pretty much not allowing it to come in there. So I don't think it's written into our codes at all, where it's allowed to come into it, but I do know that the aluminum industry or the wire industry is making a push for that as well. So aluminum wire is considered an increased fire hazard, plain and simple. We're going to go through a lot of these terms as well. We're going to hit that grounding and bonding again as we go through these things and get a few different definitions in here. All right. I'm not going to go as heavy as I did earlier on this, but grounding, or ground, as I mentioned earlier, it's an intentional connection to the earth. All right. It does give us lightning protection. It creates an electrical reference point, and that reference point is what we're going to call zero. So when I say it creates an electrical reference point, I'm really saying that it makes a zero potential, or whatever the earth is. All right. It makes everything else that's touching the earth become the same potential as the earth. So since we're going to call the earth zero, everything else that's grounded is also going to be zero. So if I touch two items that are both grounded, they're both going to be the same potential. They're both going to be zero. I am not going to be a conductor that's going to equalize those items out. All right. Offers protection from ground fault circuits. And this one I have to disagree with a little bit. It doesn't really give us protection from ground fault circuits. In fact, if we had a ground fault, it's the bond that gives us the actual protection. And when we talk about the bond, we're talking about the connection between the main bond, which is the connection between my grounding system and my neutral system. Because we stated earlier that if I only have 5 amps of electricity flowing into the earth, then that's not going to be enough to trip the breakers. So what I have to do is get that ground fault, all right, because electricity is going into the earth when it's not supposed to, so that's a ground fault. What I have to do is get that ground fault back onto the neutral, or the grounded conductor. If I can get it onto the neutral wire, now there's no resistance on that at all. Whatever electricity is available on the system will attempt to flow. Far more than that 5 amps that the earth is going to allow. Far more than 15 amps that the breaker is going to trip off at if I go over 15 amps. Even if that 15 amp breaker is broken, it's going to be far more than the 100 amp or 200 amp main disconnect breaker. All right, we're going to have I really don't know what the number is, but it's far greater than that 200 amps. In fact, it's so much that even if the 15 amp breaker is bypassed or overridden and the 200 amp breaker is damaged and that's not tripping off, there's going to be so much electricity flowing at that point in time that wire is actually going to catch on fire. It's going to burn up. And it sounds like it's dangerous, but in all reality, it's a good thing. Because if it catches on fire, it breaks. And air is a resistor. Air is enough to keep electricity from flowing. If I keep two wires far enough apart, electricity will not flow. If I get them close enough together, we're going to start getting sparks, like lightning. So when we get the air, there's no electricity flowing. But if there's enough voltage to jump the air, then we'll get it to go ahead and flow on there. So what we want to do, is burn that wire up if we can't trip the breakers. I mean, breakers are our number one priority. Trip those, turn the power off, everything's safe. If they're broken or damaged in any which way, we burn that up or break the connection. We don't allow for another person to get shocked or electrocuted. We don't allow for that constant flow of electricity to get heated up and start creating and putting the structure on fire. All right. So grounding does not necessarily give us that protection from ground fault. So that one I kind of want to dispel. Bonding does. All right. So going back to bonding, item to item, makes two things the same potential. All right. I want you to also know what the main bond is. All right. For most city water systems, our main bond is going to be located at the first means of disconnect. So wherever that first main panel is, the first thing that I go ahead and turn the power off on, that's where my bond's going to be. In my home, my disconnect is located outside in the meter panel. So I'm going to have a grounding electrode conductor coming out of that and going to my water pipes. I actually have a secondary ground that goes to a ground rod that's right below it. All right. That doesn't, even though it's tied into my distribution panel, my main distribution panel does not have another bond in it. So my grounding electrode conductors go from the first means of disconnect. In my case, it's outside. Most homes, it's going to be wherever the main panel is going to be located at, and that first main disconnect that's there. The two systems that we're connecting is my grounding system and my neutral system. So that if any wire that comes loose, it's going to energize the case, and I guess I should back up and make up a make-believe object. So let's say we have an electric dryer, all right? That electric dryer has wires that are built into it. If one of those wires that energizes the motors comes loose in there and falls and touches the case or the metal container of that dryer, it's going to energize that dryer, or at least the case of that dryer. Even if it gets stripped free of the insulation and that rubs on the dryer, that's also going to be energizing the dryer, all right? If that dryer has a ground plug, so a 3-prong plug on there, that ground plug is going to be energized. So we energize the case, the ground plug or prong is connected to the case, that's energized. That's going to be energized to the junction box, to all of my conduits, all my plumbing pipes. All those items are connected together. So as soon as I have an energized conductor energize the case, it actually energizes all my plumbing system, all my conduits, all the cases, and everything else that has a ground plug that's plugged into, any grounded outlet. All those items are instantly energized because I have one loose wire touching that. I'm hoping you can see how dangerous that is, and we need to turn that power off as fast as possible to keep everything safe coming in there. So what we need to do, if I need to get that electricity back over onto the neutral. So my main bond connects my grounding system to my neutral system. My grounding system will only flow 5 amps, not enough of a flow to go ahead and trip the breakers. So I need to have unlimited flow of electricity or unlimited flow of amperage to go ahead and allow that breaker to trip. All right. So in this situation, we'll talk about bonding, and we'll get into that again, and we'll build a bond in the sub panels how we don't bond. I made a comment earlier about faults. Faults is anytime electricity is doing something that it's not supposed to be doing. So typically with breakers, we're going to have an overload fault. So in here, they're showing that we're putting a 50 amp load or any type of work more than what that breaker is allowed to handle. And if it's a 20 amp breaker and I'm trying to flow 50 amps through it, that breaker should sense that and trip and turn the power off, so now no electricity goes through it. Phase to ground, that only works, and if we follow the power back, wire comes loose, just the way the electric dryer that I may mention, energizes the conduit. As long as that conduit is attached to my box, it's going to energize the box. On the bottom, there's a bar that connects my 2 neutral bus bars, and you'll see a green screw in there. All right. So on the bottom, that green screw actually goes right into the neutral bus bars where that metal's connected to it. It goes through the gray or black plastic insulation. So the insulator is the black plastic so that it separates my ground, my neutrals, and everything, and my energized conductors and my bus bars. It keeps all those separated. And then it keeps going through that all the way into the back of the panel. So it screws into the panel. So if my conduit is energized, my box is energized, that bonding screw is energized, that bonding screw is connected to my neutral bus bar, now my neutral wire is energized. Now I don't have any sort of resistance at all. Whatever's available on the system will attempt to flow far more than that 20 amp breaker, far more than the 100 amp main disconnect. So those should trip right away. And even if they don't, then we're going to go ahead and get a burned up wire, which will actually break the power as well. So the second one is a short circuit. also known as a neutral fault, and I should say the third one going down there. That's a neutral fault. That one's real simple. I take the hot and I touch it to the neutral. I don't have to worry about anything else. I'm trying to flow whatever is available on the system. Again, more than with the breaker, more than the main breaker. Those two will pop, or one of the two will pop. And then if they don't, then the wire will burn up. And then we have a phase to phase. Both of those are considered short circuits. You know, if we're going to have a phase to phase, a hot to hot, that voltage separation is going to be bigger. So the phase to neutral short circuit, that's going to have 120 volts and it's going to create a 120 volt spark. If I have a phase to phase short circuit, that doubles the voltage, doubles the size of the spark where it comes into it, but it's still going to trip the breaker. And that's the big audacious goal. Get the power turned off. Anytime that the electricity isn't going where it's supposed to go, we want that power to turn off as fast as possible. Sometimes we're going to run into houses where they're older homes and they didn't have grounding systems in there. The old outlets were 2-prong outlets that came in there. This isn't the best practice, and the drawback with this is many of those 3-prong testers we use, we don't really find it. You know, this gives me one of the cases I make for why I like non-metallic cable. When we're dealing with non-metallic cable, for the most part, they're going to have an energized, a neutral, and then they're also going to have a grounding wire in there as well. So if we end up replacing some of these things, then we can still make sure that everything is grounded. Now, will this work if I have a wire come loose and an energized case? Yeah, it will. All right. That will go ahead and get the wire over to the neutral. But in all reality, because the neutral always carries amperage, we said amperage doesn't disappear, and if it's 120, doing something like this is basically the same thing as bonding a sub-panel. We're putting that particular ground and that particular neutral together. And if I have another ground path coming in there, I'm actually inviting amperage on my grounding system. And that we just don't want to do. Not to mention, if somebody wires this outlet up wrong, and they do it in a reverse polarity, and I'm sure that anybody who has experience in this, we run into a lot of outlets that people just don't know that the brass screw gets the black wire or the energized wire, and the silver screw gets the neutral conductor, and the green screw gets the ground. If somebody flips those backwards or disconnects it and reconnects it, now I'm energizing the case of whatever I'm plugging into this outlet. And to me, it's just dangerous, all right? We want to keep our grounds and our neutrals separate everywhere except at that one location and that one location only, and that's our main bond, and that's, again, going to be at the first means of disconnect. A little bit more on outlets here. You should have a rough idea of which slot is which and which screw and how many amps each one is designed and so forth. So the first one on the left, we can see that both slots go straight up and down. All right, we do have the round cave-like one, and the cave-like one is going to be my ground prong or my ground slot that comes in there. So that green screw that's on the bottom left, both of those ground ports, I guess, go to that green screw. It also goes to those metal tabs at the top and the bottom, and those screws that are in the top and the bottom. Those are all tied into the ground system for that particular outlet. So many times, because in conduit areas like where we live here in Chicago, we're not going to run separate ground wires to these outlets. We use the conduit that comes in there. So we really don't make a connection to that ground wire or that green screw on there, because those little plates that are at the top and the bottom, they're screwed into the 1900 box or the outlet box on there. And as long as I have a metal connection, then that outlet will be grounded, plain and simple. The narrow slot on the right-hand side, that's for the energized conductor. If you look at the screws on the right-hand side, you'll see those screws are brass screws that go in there. The wider slot on the left side, that's for my neutral conductor slot. And you'll see the screws on that are silver. So the black wire goes to the brass screw. The white wire goes to the silver screw. And if it was a non-metallic system and I had a ground wire in there as well, then the ground wire would go in there. Now, if you notice, it says off 15 amps underneath it as well. All right. Whenever I have the neutral slot and the energized slot, and they're both going straight up and down, that tells me it's a 15 amp outlet, plain and simple. And I take the next one in there, and you can see how it's shaped like a T up in there. So if I have the energized conductor straight up and down, and then I have the neutral slot horizontal, that's for a 20 amp outlet. All right. When I get the T, as we're showing here, that's telling me that it's either 15 or 20. It'll work on either one. I could wire it up to a 14 gauge or to a 12 gauge. And I take that back. I should have only a 12 gauge wire going to those. And you will find that back on a lot of 14 gauges. Going off to the right, even more, we start seeing 240 receptacles. And these 240 ones are going to have the energized conductor slot on a horizontal phase. All right. So that's going to tell me that's a 15 or 20 amp plug, and that's going to be for a 240 volt circuit. The bottom one is kind of a split receptacle, and the bottom one here is designed for a 240 circuit, where the top one is only designed for a 120 circuit that comes in there. So you are going to see some weird and awkward outlets, but I'd like you to be able to determine what's what and what they mean. All right. So again, these are just single dedicated outlets. So the one on the left is going to be our 15 amp. The one on the right will be our 20 amp. And only because we have that horizontal plug. All right. This is probably about the safest way to put a plug on there. What is missing is the actual cover plate that holds the actual outlet itself. Right now we just have a 1900 box. There's supposed to be another plate on there that I could screw the top and the bottom of the outlet on there. But at least they went ahead and they put another ground wire from the outlet to the box on there. And as long as that box and all the conduit going backwards is all connected, then even if I remove that outlet, I am still grounded. All right. Otherwise, if that outlet was loose and free, it wouldn't be grounded. The only way I would be able to ground it is to get those metal prongs touching it again. All right. All right. Typical circuit. We come off our panel. It's our energized conductors. Goes to the energized side of the bulb, and we got a neutral coming back. That's going to be the separation is 120 volts. Typically what we end up seeing. Electricity flows in. Lights up our light bulb once we get our complete circuit. So again, if this light bulb is a 120 watt light bulb and I have 120 volts of service, that means I'm going to have 1 amp of electricity being used to go ahead and work that light bulb. That 1 amp will be measured on the energized conductor. And if I put an amp meter on the neutral conductor, I will also measure 1 amp on that as well. I don't need the ground wire to make this circuit work. What we want the ground wire for is just in case that electrical, the hot or ungrounded conductor, the energized conductor, in case that comes loose and energizes something, we need another pathway to catch that and trip the breaker. And again, we need to have that bond in order to make that happen. So let's build up a multi-wire circuit here. We're going to take one of our hot breakers and slide that into place. We'll take our other one and we'll slide that into place. We'll go ahead and we'll take one of our energized conductors. We'll run it to our light bulb and bring the neutral back. And we'll bring the neutral back to our neutral bus bar. All right. 120 watts on our bulb. 1 amp going out. 1 amp coming back in. Plain and simple. Now we're going to do what we call shared neutrals here. So we're going to have another light bulb that goes on there. We're going to hook that up to our opposite breaker, all right? And I guess I also want to take a moment here and talk about that staggered bus bar that we're looking at inside of our panel. So you could see that the bar on the left is taking power off of the top breaker. The bar on the right is taking power off of the bottom breaker. And I'm talking about the main disconnect at the very top of this diagram, all right? So when I have these two breakers right next to each other, even though they're both on the right side, just because of this staggered bus bar, the bottom breaker is taking its electricity off the left side. The second from the bottom breaker, or the one where the red line goes to it, is taking its power off the right side. So they're both opposite phases. One's getting when it's positive, the other one's negative. So now we energize that on the opposite phase. We bring our neutrals back in here and everything back. Both light bulbs are going to work, and we made our connection. Between the two connections, we have 240 volts, but because I connected the neutrals on there, that's going to keep both of those at 120 coming in there. So if each one of these light bulbs is 120 watts, that means each one of these light bulbs is going to allow 1 amp of electricity to flow. 1 amp is going to go into the light bulb, each one of these. 1 amp is going to come out of the light bulb on the neutral, each one of these. When I get to that point, that little black dot on there where they meet at that point in time, now I'm no longer going to have any amperage flowing down that wire. All right, they're both going to cancel each other out, and then we're going to end up having 0 amperage from that point forward. However, if I disconnect that neutral conductor, now think about what I just did. I have electricity on alternating current going in one, flowing down the neutral of the other, connecting to the neutral of the next light bulb, because I'm not connected to my neutral bus bar any longer. Now, in theory, I ended up creating a 240 volt circuit. Those bulbs are not designed to carry that much voltage. They'll probably end up burning up real quick, and that's where our problems are going to be. So here's just another bit of math. It's basically to saying the same thing with bigger numbers. If we have a 1,000 watt load, and I always like to say, use numbers of like 120. It just makes life easier. But a 1,000 watt load, I divide by 120 volts. That's going to give me 8.3 amps. That's how they come up with it. So 8.3 on each energized conductor, 8.3 on each of the neutral conductors, 0 amps after those two neutral conductors came back together. This is actually called sharing neutrals, all right? So if I have less wattage or less amperage being used on one side than the other, now I will have amperage flowing on the ones that are shared. And this is part of the reason why in those electric stoves, we end up needing to have a neutral wire coming back in there, because I'm going to have those 120 volt circuits such as light bulbs and computers and timers, things like that aren't going to be 240. So they're going to be unequal, and I need to bring the balance back. So whatever the balance is, left side 8.3, right side 4.1, the balance is 4.2. That balance is what's going to be brought back to the neutral bus bar. In order to get the full load, only one side has to be running electricity while the other side is not doing anything. Then we're going to have the full load of one side. Neutrals. Neutrals cannot be cut to make this type of splice at the receptacle on a multi-wire circuit. Okay. And they're supposed to be stripped back of the insulation and then kind of flipped over it. What we don't want to have somebody do is unscrew the wire, and then all of a sudden it ends up creating a problem. Notice the upper wire, the feed is burning up. It's starting to overheat. Continuity was stopped, and that ended up creating an open circuit on there. And once we open that up, now we're creating 240 volts circuits where they're only intended to be 120 volts, and that's when you're going to start getting things overheating. All right. Now this one, if you look back at the panel, you can see we moved that second breaker up a slot. when we did that, now both of those breakers are taking power off of the same phase. Now we said before that amperage will cancel each other out, but in this case, since they're both on the same side, they're not opposites any longer, we're going to be adding them up. And now we're going to start overloading. So if I got a 20 amp breaker and 12 gauge wire, and I'm running 12.5 on one side, 12.5 on the other side, since they're on the same phase, we're going to actually add the amperage at this point in time. So on that neutral, because amperage doesn't disappear, it will add up, and you're going to end up having 25 amps. If you have a neutral wire where you see heated up, chances are, and sometimes when you look at these panels, it's hard to tell what goes where, when, and how, but there's a pretty good chance one of two things is happening. Either it was a shared neutral circuit, and they got the breakers on the same phase, so they're not on different phases coming in there, or I had a loose connection. That happens when we start double tapping and triple tapping underneath that neutral bus bar, and that starts creating resistance. Anyway, my neutrals are heating up, and these connections are burning, and it actually started a fire, a small fire, but a fire nonetheless inside that panel. Another multi-wire circuit. And when we deal with multi-wire circuits, if they're in different boxes, I don't have to tie them together. All right, I could keep them separate. All right. So we got shared neutral, multi-wired circuits. The black wire coming up at the top feeds the two right outlets. The red wire feeds the two left outlets coming in there. As long as the amperage is the same or whatever it is, the neutrals are going to only carry the balance, if anything, back to the neutral bus bar. All right. I do not have to have a 240 circuit or a 240 breaker on this situation. However, if I decide to make one of those outlets a split receptacle, all right. So now what I did was I separated the top and the bottom of the outlet, and I feeding the top outlet off of the red wire, and I'm feeding the bottom one off of the black wire. They're both coming off of two different phases. I'm still bringing one neutral wire coming back in here. Because that's in the same junction box, I have to tie those two together. All right. The rationale behind this is that if I turn the breaker off to one, the entire thing needs to be dead. I don't want somebody going in there and working on this and then thinking it's dead when actually it's energized by the other breaker that comes in there. All right, so if I have a split receptacle from two different breakers and they're sharing the neutral coming back, or even if they are from two different breakers and they're not sharing the neutral, they have their own neutrals coming back in there, they need to be tied together. So when I turn the power off to that box, everything needs to be turned off. All right, the old standby, a lot of people use these 3-prong testers. They, for the most part, they're great. All right, they're quick, they're fast, they give you a result that comes in there. And sometimes when you look at them, you could see that it's doing something a little awkward or a little bit different that comes in there. So if you see one of them is dimmer, one light is dimmer than the other light, that usually tells you that you're going to have like a bootleg ground or somebody's doing something awkward. The one thing that I have found, and I didn't test this personally, I just saw it in another video somewhere, is that if this 120 volt outlet is accidentally wired as a 240 volt outlet and it's properly grounded and you plug this in there, supposedly it's going to show normal. You're going to get 2 yellow lights and everything's going to show correct on there. If you get the more expensive testers, that's going to pick that up. I myself have never run into that, but who knows if I would have noticed it if it was, because I don't take each outlet apart to look at the inside wiring. All right. But anyway, if one light in the middle, open ground, open neutral, is the light on the right. Obviously, if we don't have any electricity come to it, we don't have the energized conductor operated. Anytime you have a red light up there, that means we're going to have some sort of reverse polarity. whether it's a hot neutral reversed or a hot ground reversed. Either way, it's going to be some sort of a neutral polarity. So basic home inspection procedures. They say we are supposed to look at a representative sample. You should know that definition. A representative sample is basically one per room, or one on the outside on each wall. That's the minimum that we actually have to test. All right. If it's more than that, there's nothing wrong with that. You know, quite frankly, we try to get every single outlet that we can. Now, I'm not going to tip over china cabinets or move furniture to get to them, but if it's out in the open or I can reach to it, I'm going to go ahead and do it. I'm not going to unplug anything in order to get to the outlet, but I'm going to hit as many as I can. So I don't want to do the minimum. I want to do as much as I can, knowing what the minimum is, and that's the least that you have to do when we come to it. Our industry standard is non-invasive. The 3-light tester provides for that. Can it be fooled? Yes, it can. Can we get a safe, normal reading on the 3-light tester and have a serious problem? Should we be using a more thorough instrument? That's going to be your choice, all right? Right now, there's nothing that says we have to, all right, use anything other than what's on there. All right. So what I'm going to do here is we're going to build this air conditioning system that's present here. And it's a typical connection that we normally see. And we want to talk about, is it going to work? Is it safe? What's going to protect us? And so forth. Now, just for the illustration, obviously we don't have conduit going from one to the other. But I want you to imagine that it's there. The only reason why I didn't do that is just so I can make it clear with the wires and so forth that's coming to it. All right. So I got a central air conditioning compressor cabinet outside. I have a disconnect panel that's going to it, and it's connected via conduit on there as well. Typically, that's going to end up being seal tight. I do have one red wire, one black wire, so we have phase A and phase B is connected to it. All right. I do not have a neutral that's connected to this. So the first question I always like to ask is this thing even going to work? And the answer is going to be yes. Right now there's only 2 motors that's inside that air conditioner. One motor is for the compressor that's compressing the refrigerant, and the other one is going to be for the fan that's going to be blowing the air up going across. Both of those items are 240 volt items. So because they're both 240 volts, they will be using the same amount of amperage on both sides of the fields. If I had a neutral wire on there, I wouldn't have anything flowing down the neutral wire, so I don't even need the neutral wire coming in there. So yes, this will work. Is it okay? Not only is it okay, it's a very common setup that we end up seeing here. Next question. There's no ground. All right, so is that okay? All right, so let's say there's no ground coming in there. Our problem now comes into play is if I get an electrical energized conductor come loose, and that conductor now energizes the case. That case is going to energize the air conditioning cabinet, the conduit, everything there except to where that ground is failed. So even when I'm checking air conditioning units, if it's the metal seal tight and they're using that as a ground and they didn't run a separate one in there, I make sure those are tight and secure. If it isn't, then I want to make sure that there's another ground wire that comes in there to make sure that I have that ground path going back. In this situation, I'm going to, once that energized conductor comes loose, touches the box, my entire air conditioning system, over here is ending up energized, all right? So if everything here is energized, then I'm not able to clear that fault. If I had a ground wire coming back through it, then that ground wire would bring electricity back to the neutral, down, and get it, back to the case, get it to my neutral bus or neutral bond on here. The bond would get it onto the neutral bus bar. That would allow my free flow electricity, and that's going to go ahead and allow everything to clear the fault and allow the breaker to trip. And that's our big audacious goal again. We want that power to turn off as fast as possible. So here we're showing if it stays energized, then whatever is going to be touching there is going to be remaining energized. We're not going to have enough flow to go ahead and trip the breakers, and that's where our problems come into play. And you still get shocked and electrocuted. So now we took a green wire, we ran a ground to our grounding bus bar. We do have our bond inside there as well. So now that wire comes loose and energizes our case, which is going to energize our ground wire. Because that bond screw is there, it's going to now energize my neutral bus bar. That neutral bus bar allows for no resistance whatsoever. So we're still going to have 5 amps go down the grounding electrode conductor, but we're going to have unlimited amps going up the neutral wire. That unlimited amps is going to be far more than the breakers, so they should be tripping instantly, and then our power's turned off and nobody's going to get hurt. That's our main goal. Different types of grounds I'd like to talk to. In the Chicagoland area, we use water pipes. And think about it. You got miles and miles and miles of underground steel, lead, copper, unlimited pieces of metal that's underground, which are fantastic conductors and are going to allow everything to flow quick and easy. We're still going to be limited. All right, that's still going to only limit 5 amps of electricity to flow because it still has to get from that over to the transformers. So getting from those 2 points is where our resistance is going to end up being. All right. Yeah, there's just not enough electricity to flow to clear the path. All right. Different types of grounds. Let's go back to this one here. And different types of grounds that we're going to run into. So here it mentions the water pipes. We already talked about the ground rod outside. Some areas of our country, they don't have soils where they could dig into. Sometimes they're on bedrock and they can't take that piece of steel in there. Sometimes it's going to be on a slab. Different things that we can use for a good connection to the earth, item to earth. Well casings. All right. So if I got a metal well casing that goes down, I could ground to that. I could do something called a ground ring. So I would end up taking a number 6 or a number 2, depending on the size of the electrical system, and it would be a bare copper wire buried about a foot underground going around the entire perimeter of the house. That's called a ground ring. A ground plate is basically a 4x8 sheet of metal laid flat, covered in dirt. All these are good connections. An oofer ground is another one. That's where I use the steel rebar that's in the concrete, and I'm going to use that as my connection to the earth. All of those are acceptable, all right? And all of those are going to help me dissipate lightning strikes, and then they're all going to also help me maintain that zero potential. Bonding, on the other hand, we talked about item to item. When we talk about the main bond, all right, or, I hate to do the quotation mark thing, but when we talk about the bond, that's going to be located at the first means of disconnect, all right? That bond is going to be connecting 2 distinct items. So we said bond is item to item. When we're talking about the bond or the main bond, we're connecting the grounding system to the neutral system. We're doing that so that if I do get a ground fault anywhere, that's going to allow free flow electricity, and we're going to basically change it into a short circuit, and that's going to be tripping the breakers. Without that bond, we're just going to be flowing electricity into the earth. We're not going to have enough flow to go ahead and trip the breakers. So that bond is vitally important. When we open up our panels, the first thing that we're going to look for is the bond. I want to verify that I got my ground connection to my neutral connection. That's how I know that if there's any wires that come loose anywhere that I can't see, at least I got some sort of a pathway, maybe. That I have a pathway at that point in time to get it onto the neutral system. After that, the next thing I'm going to be looking for is my grounding electrode conductor, all right, or my GEC. That is also known as my ground wire, but that's a specific ground wire, all right. That's going to go from the location where the bond is to wherever I'm going to be grounding this to. So whether it's a ground rod, whether it's a water pipe, ground ring, oofer ground, ground plate, well water pipe going in there, whatever I'm grounding my house to, that GEC is my connection from the main, where the main disconnect, it's my connection from there to whatever I'm grounding to. That grounding electroconductor does have some specific rules to it, all right? And I don't have them written down. So if you have a pen and paper, I would suggest that you write the following down. I'll try and go a little bit slow. Depending on the size of the electrical system, tells me the size that GEC needs to be. GEC, grounding electroconductor. All right. If I am less than 150 amps, then that could be a number 6 copper wire. Less than 150 amps, a number 6 copper wire. Greater than 150 amps, it needs to be a number 2 copper wire. 150 amps or more, I should say, it needs to be a number 2 copper wire. That GEC is not allowed to have any splices in it whatsoever. All right. So when I identify it and I follow the conduit or I follow the GEC going wherever it goes, I want to make sure that it's not cut and I don't have 2 connections under a mechanical splice. I'm not allowed to do that. There is one way or one type of splice that I could do. It's called a pressure splice. And they'll put a hydraulic tool on 2 pieces of wires and they'll squeeze the living daylights out of that thing until they meld it into one wire. All right. So there's no screws. There's no mechanical connection. They just squeezed it and basically made it into one wire. You would have to literally cut it with cutters in order to break that connection again. So if we could break a connection with the screw, it's wrong. If we have to cut it, then that splice is okay. And those splices don't have to be in a junction box. So as I follow that out, if I run into a junction box on my ground path, I should be suspicious. And those are going to be the areas that I'm going to open up. And if you get inside that thing and you see your GECs are spliced together, that's a problem because we're not allowed to splice those whatsoever. All right. They have to be, if they're going to be in conduit, they have to be in conduit by themselves. All right. We can't use that raceway to share with other electrical wires. They have to be standalone all by themselves. So if I'm having trouble finding my GEC and I'm inside the panel, one of the things I could look for is in my conduits, there should only be one, maybe 2. You know, if they go one to the water pipes and one to a ground rod outside, I might have 2 of them. But they should be one wire inside that conduit all by itself. All right. If any other wires do share and go in there, that's going to end up being a problem. Nothing else goes in that GEC by itself. If the GEC has insulation on it, all right, then that should have a mechanical connection because we want to use the conduit as well that protects the GEC. We want to use the conduit as part of our grounding system. So we need to have a mechanical connection pretty much at both ends to the conduit. If it's not does not have insulation, so it's a bare conductor for the GEC, and you will run into those are not required to have a mechanical or a metal connection at each end. So we don't have to tie it to the conduit. It makes sense because obviously if it's bare through and through, then most likely it's going to be touching that conduit in multiple places that comes in there. So no splices, number 6 or number 2, 150 amps is my line in the sand. Nothing else shares in the conduit with it. In Chicago, we have something called a Chicago ground, And they did that in a lot of the suburbs around here as well. So they'll come out of the electrical box, usually at the first means of disconnect, and they'll go to the closest water pipe. And when they get to the closest water pipe, then that's where they're going to attach their ground system or grounding electroconductor to that water pipe. From there, I need to follow that water pipe until I leave the building. If I have any sort of dielectric unions, or I'm switching to plastic pipes or something like that, I've lost my grounding connection. So I have to have jumpers over those if need be. When I get to the water meter, I want to make sure I'm jumping over the water meter as well. Because there's going to be a time when the water meter might, if the house gets foreclosed and the water meter gets removed, we don't want the person who's going to be connecting it together. They're going to touch one side that's going to be 0. They'll touch the water main that might be something different. And once they touch those two different objects, if they're different potentials, then that electricity is going to flow through them before they put it together. So we need to have a jumper cable that's loose, connected. When I say loose, I mean the wires aren't wrapped around it really tight. The connections are tight and secure. We should actually be moving those to make sure that they're tight so that I know I got a good connection between the between both sides of my jumper cable. All right. Ground bonded to neutral to go ahead and clear the fault path. Good. So there's our bond screw, and these are just different examples of what we're going to see on the bond. And again, we're tying right below that. It's going to be my neutral bus bar. All right. So this whole thing over here is my neutral bus bar. And there you can see where my bond screw is. So that screw goes through that metal bond or metal bus bar. It goes through the black plastic insulation right there, and it ties into the metal box that's behind it as well. Now that metal plate runs behind the neutral and the energized conductors, and then it also ties into this neutral bus bar on the left-hand side. That is my bond. So if anything energizes my grounding system, that's going to allow electricity to get over to my neutral system, and then I'm going to have free flow electricity enough to go ahead and trip my breakers. This is known as a bond screw. Sometimes we're going to see a bond strap in here as well. That's this item down here. So that bond strap, again, goes into the neutral bus bar, ties to my box. Any electrical wires that come loose and energize. I see that, Mark. I'm going to bring that up in a second. Anything that's tied to both, anything that ties to both again are going to go ahead and connect it. So if any energized conductors come loose, energize my box, then that's going to go ahead and energize my neutral wire. All right. We do have one question up here, and let's see if I could pop this on here. And it doesn't want to play nice to me. All right. So one of the questions Mark asked, if the water pipes aren't used for grounding, then is it still important to jump past the water meter? And the answer is going to be yes. Because even if the water pipes aren't used to it, if I have, and especially in our area, if I have a water meter there, it's very common. So the utility companies are going to be expecting to use that as well. If the utility companies, such as the phone company, cable company, satellite dish, they all have to ground their items as well. So they may be going ahead and grounding to the plumbing pipes. They may go ahead and ground to the meter box outside. Whatever it is, the expectation is there that those items are grounded. And not only that, but if somebody is outside and they're going to be touching the plumbing pipes inside and something's disconnected, we want to make sure, because all those pipes are metallic. I'll even go one step further. You know, we should actually be bonding our water pipes to our gas pipes. In some communities they do that, but in many communities they don't. And the whole idea there is, again, if somebody touches the gas pipe, because they usually run right by the water pipes, if they touch both of those, we don't want them to be different potential. This is a pushmatic panel, and some panels are really difficult to be able to find that bond screw. That's not always going to be that big fat green screw or that bonding strap that we saw earlier. This one here where that arrow's pointing, that's actually my bond screw. It goes through the neutral bus bar, which is all those screws above it, and it goes into the panel in the back. There's going to be a schematic, unless it got pulled away or damaged or whatever. There should be, I should say, a schematic on every panel that shows the neutral bus bars, the breaker bus bars, and on there you're going to be looking for a phrase on there that says bond when required, and it's going to be pointing to a certain hole or slot. That screw needs to be filled in there. Now, we're not going to know if they put the right screw in there. Somebody could have put the wrong screw and it doesn't go all the way through. We're not going to back these things out and verify it. But we should be able to verify that most likely it is there. In this case, on the Pushmatics, that little screw there to the right of the GEC, that's going to be my bond screw that comes in there. Here's our typical water meter. This is a lead service main coming in here. As we come up, you can see I have my GEC, my grounding electrode conductor. It does have insulation on it, so the insulation is stripped back. That wire is not cut. Remember I said we're not allowed to cut or splice this GEC at all right? So it's not cut, but the insulation is stripped back. That strap that's on there connects it to my conduit, and it also makes a solid connection to my water pipes on the street side of the meter. Again, the connection where the wire is fed underneath there, the insulation is stripped away, but it's not cut, and then we jump over to the left side of the meter. Something else too, just throwing this out there, that tamper wire on that water meter, I kind of look for those. Many times you're going to find a tag on there where it's like a $500, $750, or $1,000 fine if that tamper wire is cut. And I can't tell you how many times, actually I would guess to be around 20%, so 1 out of every 5, I find where either that tamper wire is missing or it's cut. Some communities don't require it, and some do, all right? But I would still let my client be aware of it. This way, they're not going to get stuck in case for some reason a meter reader comes inside and sees that that's missing. But for us, in this class, we're talking about the GEC. That GEC, in this case, is probably about 100 amp service because that looks like a number 6 copper wire. And it needs to go to the street side of the meter and jump over the meter. This one here, same thing. We connect it, we're on the street side, but we don't have a jumper wire coming back. All right. So here's another view of the same picture. Our water line's coming in. We're connected to the street side, but I don't see anything that is taking it from this side of the meter over to this side of the meter. All right. And we should have some sort of a jumper. And also, remember what I said about the tamper wire. This one was also cut. I think this is a great practice as well. I'm seeing it more and more communities, which I'm pretty happy with. So they'll jump over or bond both the hot and cold water side of the water heater. Usually I'm seeing that same wire will continue on and go to that gas pipe that's to the left. So they'll put all 3 of these together and make sure they're all the same potential. And again, if somebody has to switch out this water heater, once you remove that water heater, you break all the bonds of those different items. Not to mention we got dielectric unions on the water heater as well. So these dielectric unions that you see down here, those have little plastic pieces that separate that in there. So I really don't even have a connection to my water heater at this point in time. The electrical potential and all the connected metal parts needs to be the same as the earth, plain and simple. Anything that's different, we're going to take a chance for electricity to flow through a human being. We don't want that to happen, so we need to maintain that we're properly grounded so that we keep that 0 potential. All right. Lightning strike, same thing. I want to give a pathway for that electricity to get into the earth. sub panels. All right, and this is another important one. We do not want to combine or bond our grounding system to our neutral system in a sub panel. We should have separate grounding conductors and separate neutral conductors when we come through it. The reasoning goes back to the amperage not disappearing. So if I'm inviting amperage to go on the neutral, and we'll get back to slides that show that a little more clearly. In fact, here it is. Let's start building it, and then we'll talk about it. So I got an energized conductor on a breaker, phase A. I go ahead and connect it to my bus bar and my sub panel. I take phase B, connect that to my bus bar on the other side. So now my panel's got a 240 panel on the right side. I'm using the disconnects in the bottom of the left panel in order to make all this happen. I run a separate neutral wire. Everything is good at this point in time. I'm going to bond and ground my main panel at that point in time. So I just popped the bond up there, and right before that I put the GEC in there. Now I have a regular electric circuit. We have a hot and a neutral going to it. I'm still in a conduit system, so my conduit will be my grounding system. We're going to keep everything separate at this point in time. All right. So energy goes in through the hot, comes back on the neutral. The amperage is still flowing on the neutral. Neutral goes up and out. No problems, normal conditions, nothing, no problem whatsoever to see here. So now what we do is we're going to throw a bond on the sub panel. And again, this is going to be under normal circumstances that's happening here. So what we're going to do is energize that outlet again. So we're going to be doing work. Amperage does not disappear. So we're going to energize our energized conductor, and then amperage will be on the neutral. Amperage or electricity is going to flow in any means possible. All right. So yes, it is going to flow on the neutral. No doubt on that. But because I'm bonded there as well, I'm putting a connection to my electrical panel. Electricity is also going to be flowing on my electrical panel as well. All right. So now I'm going to have amperage where everywhere between, as long as electricity is flowing and how much amperage is being used, I'm going to have amperage on my conduit system between the panel and the sub panel for whatever is being used. And if somebody touches that and something else that's zero, then they can go ahead and start creating an ulterior flow, and they can actually get themselves shocked or electrocuted. All right. So having that secondary bond, I'm sorry, it's not good. All right. Plain and simple. Now, either way, with or without the bond, if I had that ground fault and everything else was connected, all right, I would still be good. So here we're showing a phase, the case fault, energizing my case, energizing my panel, energizing my conduit, energizing the other case, energizing my bond, and that gets my power to the neutral, free flow electricity. My breaker is going to go ahead and trip. This is all good, so it's not going to harm us there. But the biggest problem is we're inviting electricity under normal usage, not under a fault usage. All right. On ground rods, if we do use ground rods, and it is acceptable, and there's some areas they only want that. If you have a single ground rod that's being used, then there needs to be an ohm test. All right, it has to allow for a certain amount of resistance that needs to be done, and it's a little bit of a process, costs a few bucks. It has to be done in the presence of the inspector, at least I think it does. Bottom line is nobody likes to do that. It's simpler and easier just to go ahead and purchase 2 ground rods instead of 1. As long as you have 2 ground rods in the earth, then you do not have to do an ohm test. But the same rules apply, all right? Now here we're coming out of the meter panel, and most likely this is going to be on a well system. So my bond is going to be located in that meter panel, or I have a main disconnect outside, and then this is going to be a common setup. That GEC is going to go to my first ground rod. Again, no splices. We strip away the insulation. We attach it to it. All right. And then we're going to go ahead and go to my second one on there. Sorry about that. And now the wire goes down into the earth, and it's going to connect to another one that's going to be about 6 feet away. All right. I just think it's a great idea. There's nothing bad about having too many connections to the earth. We just don't want to have different connections to our electrical system at different locations. All right. We want to keep all those separate, or all coming from the same point, basically. So this is just another connection for our water pipes. This is that Chicago ground that I talked about. Comes out of the electrical panel, goes to the closest water meter. If we have a plastic water feed coming in here, this is not going to do us any good whatsoever. All right. I would still try and get some sort of connection for these water pipes to still be part of the grounding system. So I would still go ahead and get them connected to it, but we're not going to be connected to the earth. All right. So more or less we're bonding the plumbing system to the ground rods outside, to the ground system, so they all stay the same potential. GFIs, a couple of different rules on these, and GFI stands for ground fault interrupt. You'll hear the term GFCI, ground fault circuit interrupt. I really don't care which one you use. Shorter, 4 letters, whatever. It is what it is. These are designed to protect people. They're not really designed to protect property. Breakers, they're limit the amperage that's flowing so wires don't overheat. They're designed to protect property. GFIs, if electricity is going anywhere that it's not supposed to go, these will sense that and they'll turn the power off immediately. All right. Now, I always get mixed up on how fast these things are supposed to work. I know I've used terms of 1/50th of a second, but 1/40th is the right number that's up here. But that's just fast. 1/40th of a second is almost instantaneous. We did a couple of tests on GFIs, and I remember we had a light bulb that we had hooked up to a ground rod outside, so we created a ground fault, basically, and the ground conductors and water services. All right. So I got a question. Did you cover wire sizing for grounding electrode conductors, either by rod or by water pipe? And the answer was yes, I did. So the GEC, whether it goes to a water pipe or to a ground rod, the GEC has to either be a number 6 copper, and that's for under 150 amps, or a number 2 copper for 150 amps and over. So number 6 for under 150 amps, or number 2 if it's 150 or more. All right. Getting back to the GFCIs. They need to trip off quick. We set up our sample. We put a ground rod out in the middle of the yard. We connect our neutral wire to that. We put that to the neutral side of a light bulb. We ran a hot wire to a switch, and then the switch to the hot side of the light bulb. And we had that hooked up to a GFCI outlet. All right. We flipped that switch, and as soon as we flipped that switch, that GFI tripped. We couldn't even get it to flash. We couldn't get it to even blink. As soon as we flip it, we hear the click on the outlet. It's that quick. So basically, hardly any power at all is going to be going through these things. 5 milliamps difference. That's all it takes. All I have to do is lose 5 milliamps of power, and that's going to be enough to cause these, whether it's the breaker or the outlet, cause the GFCI to trip. All right. Basically, it checks for an imbalance between the hot and neutral. This works on the same principle. Let me bring up the next slide. This works on the same principle that I mentioned earlier, that it expects the amperage that's on the energized conductor to be identical to the amperage that's on the neutral conductor. All right. So I'm going to switch cameras here, and I should have cleaned up while I had the chance. Maybe. All right. Let me go ahead and get rid of my mess here. Okay. So let's say I got, and I need you to use a little bit of imagination here. So even though I'm drawing on the whiteboard, I want you to picture this as a bird's eye view. So we're looking at a table coming straight down here. All right. So as I look down, I drill a hole in the table and I run a single electrical wire. That's what the red dot is coming through here. And this way here, north is pointing up at this point in time. All right. If I put 4 compasses around this wire, and this wire right now is not powered up, all of those compasses are going to be pointing north. Because again, the Earth is a gigantic electromagnetic generator. We have a north pole and a south pole. They're going to go to the positive side of the Earth, which is the north pole, and that's where they're all going to be pointing at. But now if I have this single wire all by itself, and now I energize it, all right, so now it's got power coming through it, and there's no neutral wire that comes in here, all of these compasses are now going to be aimed at that wire. That wire is creating an electromagnetic field that comes in there. All right. That's basically what this, and I'm going to switch back. That's basically what we're looking at in this diagram here. That ring where the 2 wires go through senses for that electromagnetic field that's being created. All right. Now going back to the drawing that I had before, if I took a neutral wire and I twisted it together and I kept it back in there, all those compasses would point back to north again. That neutral wire would cancel itself out. All right. So as we're looking at this diagram, and this is a GFCI, it is in use. It's closed, so power is on, and everything's normal. All right. So we see energized power coming in. It's going to its load. Load is wherever the work is being done. All right. And we said amperage does not disappear. So if 2 amps goes in on the hot and 2 amps go out on the neutral, I am creating a zero magnetic field in that ring. All right. Let's go on to the next one. So now we're showing that I have some sort of a ground fault. All right. So same things. I got energized conductor coming in. 2 amps is going in. 1 amp is going to the earth. And remember, it could be as small as 0.5 of a milliamp. All right. Or 5 milliamp coming in there. Electricity is going someplace it's not supposed to go. These GFIs don't know where it's going. All right. They just know it's not coming back on the neutral. Now I have an imbalance between my hot and my neutral. When there's that imbalance, those compasses now, because I'm creating an electromagnetic field at this point in time, that sensor will sense that and instantly open up that circuit, turn the electricity off to that circuit, and then turn the power off. So as long as the power is off, nobody gets hurt. All right. If the power is still on, then people get hurt. All right. And a lot of people say, well, what about these testers? Don't they, let me go back to that one there. What about these testers? Don't they, just trip the mechanism and that's it? They don't. All right. If you look at the routing from where the test button is, you could see that as we start, right here at this dot, we're going to go through when we test that button, and we're going to come back, and this resistor is going to allow 0.5 of a milliamp. So it's going to be the bare bones minimum, and it's going to bring it outside that ring. This ring is supposed to sense that difference and open up the breaker and turn the power off. So those test buttons don't just flip the switch. They actually create an internal ground fault in there. Same thing with our testers. All right. And that's another clue. If you press that test button, the GFI could be bad. They do go bad. But they might also have a bootleg ground in there. All right. So if we're going ahead and taking the electricity and putting it on the ground, and then the ground is putting it back on the neutral, it might not be able to sense that. All right. So if it trips with the button, we know the GFI itself is working, but we may not have the proper connections inside that outlet as well. So. And that works for everything downstream. So line and load, a couple more words that I guess we should know. Line side, anything that goes towards where the power is coming in from, that's the line side. Doesn't matter where I draw my line at, you know. In this case, we're going to take that GFI outlet. Anything to the power source is the line side of that outlet. Anything to where the work is being done is going to be to the load side of that outlet. That GFI is going to measure the amperage in all of those outlets, everything that's on the load side, including itself, when it's measuring the amperage, all right? So let's say that the GFI outlet at the top is using, I don't know, I'm just going to make up numbers, 2 amps. And then, so this one will be a 2, all right? And then the bottom one there is going to be another 2. And then this one will be a 1, and this one will be a 3 amps, all right, that all these things are using. So that would be a total of what? 4, 5, 8 amps, all right? So that GFI knows that 8 amps is going out, 8 amps should come back in. So even though all those outlets to the right are not actual GFI outlets, they are GFI protected. These outlets or breakers will protect everything on the load side of them, including themselves, all right? Arc faults and arc fault circuit interrupters. First thing I think before we talk on these, it should be known that the city of Chicago is not mandating that arc fault circuit interrupters be installed. All right. Most of the suburbs, at least I'm not aware of any of the suburbs in Chicago or any place else in the state of Illinois. And, you know, I hope you understand, I do not know every single code in every single part of this state or country. All right. So if some of them are following suit of Chicago, that may be true. But not everybody, or city of Chicago itself, does not require arc fault circuit interrupters. Their rationale is everything is in conduit. They have some of the safest electricity in the entire nation. I believe they're actually accurate. And the amount of damage that could be caused by these things, they feel that it's limited, so they don't want to spend the extra money and undue cost to go ahead and put them in there. It's their choice, and I'm going to respect it, plain and that simple. So what an arc fault does, it tends to provide protection from the effects of an arc fault. So basically, it recognizes that sine wave, and when something is going a little haywire or hokey with it, all right? I think it's safe to say there's 2 types of arcs when we're dealing with our electrical system, all right? What are we saying? Arc is a discharge of electric current across a gap. So anytime electricity is traveling through the air, basically, that is an arc when it comes to it. A lightning strike is an arc, all right? If 2 wires are close enough together and it's sparking across those, that's an arc, all right? It's a discharge of electricity. Parallel arcs can get extremely hot, but even a series arcs can get up there as well. It all depends on the load and how long they're going. It's a spark, all right? Any type of spark can go ahead and create some sort of a fire. So it expels metals when you see these things, and hopefully they'll evaporate, all right? So 2 different arcs I want you to be aware of. Series arcs and parallel arcs, all right? Series arcs are typically going to be the energized conductor. All right. So if there's a nick in it or a separation of the wire itself, and still enough to go ahead and get sparking, so electricity is still going to flow, that arc is only going to be as powerful as the load that's being used on it. So if I have a 120 watt light bulb being used on this series arc, then at 120 volts pressure, it's 1 amp. That arc is going to be basically 1 amp. All right. The more electricity that I use, the more powerful that spark or that arc is going to be. Whereas parallel arc, that's going to be my energized conductor and my neutral conductor. And this is what we mostly see. When they start getting smushed together and getting close enough together, then they're going to want to start creating a short circuit or a phase to neutral fault, when it comes with it. So how this happens, because we know we have conductors, we have insulators around the conductors, and then with extension cords, basically, I got 2 conductors, both of them have insulation in them, then I got another sheath that wraps the whole thing together. If I keep stepping and standing on that sheathing and I just keep squeezing it and breaking it, I mean, if you think about it, over time, I'm going to be damaging the insulation on the conductors themselves and the sheathing with it as well. And if I just keep squeezing it and squeezing it and squeezing it, and it gets weaker and weaker, electricity is going to eventually want to start making its way through the insulation once it gets damaged, and it's going to start creating a parallel arc at that point in time. Now, if it's bare bones metal on metal, then we're going to have an unlimited flow of electricity, and most likely my breaker will trip. But before I get to that point, I might just have a breakdown in insulation. So I might only have 20 amps on a 20 amp breaker that's jumping across these things, and it's constantly making sparks. And then all of a sudden it actually ignites the insulation. Or if it sparks and gets to an opening in a junction box or an electrical panel, then that could get to the wood structures of the properties. And I know most of us look for holes in electrical panels and outlet boxes and stuff like that. And I think a lot of people explain to you, look for the holes so that you're worried about people sticking their fingers in there. And, really, I've never heard of anybody sticking their finger inside of an electrical panel and getting shocked. What I have seen with my own eyes is that we create an arc or a fault inside this. We create an arc and sparks start flying inside those panels or inside of a switch box, and those holes are missing. Now those sparks get out of that panel, because those panels are designed to contain any sort of blast or arc or fault that happens inside of them. But if those holes are missing, now it gets out of there. If I got insulation, wood, anything else, there's a chance that it could start the structure of the house on fire. And that's where it comes with it. So simply making sure that all those openings are filled, it's an easy thing to fix, and it's an easy thing to look for. And granted, I get it. The planets have to be in alignment. I got to have a hole. It's got to be enough to where it ignites the wood. I got to have an arc. But that stuff has happened. And it's happened, enough times, which is why we make sure all these things are sealed. And quite frankly, I think it's a pretty cool thing that we get to do, because we get into everybody's housing inventory in the entire state of Illinois. And for simple little plugs or fill-ins, we could do everything to keep those sparks from getting out. But anyway, I'm jumping on a soapbox. I do want you to know the difference between a series and a parallel. Series is one hot wire coming apart. Parallel is the hot and the neutral pushing together. All right. Series, less likely. Current load is limited because of whatever the work is being done. Series arcing cannot be greater than the current of the load, but it still produces fire. It can still create a spark. It still produces molten lava. It still sparks, any way you look at it. Series arcing did not develop enough thermal energy to create a fire. I disagree with this statement, plain and simple. Parallel arcing, they are the most dangerous. That much I'll get. Unlimited energy until the breaker is turned off. a parallel arc is created by a short circuit or ground fault, something that's going to go ahead and start getting everything to be, getting the insulation on the conductors ruined. Now that could be whether it's an extension cord, or here we're using non-metallic cable or Romex, anything that could go ahead and damage it. So here I got a lamp cord going through a doorway. Every time that doorway closes, it's going to keep pinching that lamp cord, wearing away at the insulation until eventually it's going to create something that can go ahead and ignite that whole thing. Here, this is just a drawing I got off of, I think it was this old house or something like that. But nails going through non-metallic cable, and they can also start creating some sort of arc fault underneath there as well. This I think is a little excessive. You know, again, it was this homeowner's talking about safety of which. But if you take something that is grounded, so that drill that he has in there, so the bits, everything else, it has a ground plug tied into it. Now he goes into the energized conductor of that wire. You're going to be creating a short circuit and you're going to get sparks flowing. All right. Mostly what we're going to end up seeing is the damage of the insulation that comes to it. And that's what we're looking at here. All right. So different electrical materials and where they can be used. Kind of a short subject here. This is going a lot quicker than I thought. So we're going to be finishing up in probably about a half hour or so. Just to give you an idea. So the first thing is EMT, also known as thin wall, also known as conduit. EMT stands for electrical metallic tubing. This stuff is bendable, and usually we just get it and we could pull the wires through it. It doesn't come with wires inside of it. I do want you to look at some of the fasteners that are present on here. These fasteners, you know, such as this one right here, these are compression fittings. The compression fittings are only supposed to be used outside. What I'm going to circle in blue here, the ones with these screw fittings to tighten everything up, those are not to be used outside. Those are indoors only, all right? But the other ones are through. So depending on the size of the conduit and the pipes, determines how many wires and what size wires that we can pull through there. Quite frankly, we don't really notice too many problems with this. It's going to be really difficult to pull too many wires through this stuff. You're going to end up damaging the wires. So once it comes through, we see them damaged. Those are usually the things that we end up calling out. But it can be done. You can't pull too many through it. And then the pipes themselves are going to be hot. For those that use thermal imagers inside the panels, I think it's a great idea. See if which wires are hot. That could tell you if we're either overloading or too much bundling, or if we have loose connections. Just a nice simple thing we could do. Doesn't have to be foolproof 100%. EMT. So EMT could be used interior and exterior. Exterior has to be with watertight fittings. They're the compression ones. It is acceptable as a ground. But this is a big deal. So we don't have to have a ground wire inside of them. Now there is a push for this to have ground wires installed with conduit. And the reasoning behind this is, and I'm sure we've all seen it, is if that conduit comes loose, I just broke my ground for everything downstream of that, or everything on the work side. All right. So if this is my line side on this side, and then this is my load side, all right, and on the load side, I had a wire come loose and energize my conduit. If my conduit is disconnected, I don't have a pathway to get back to my panel that gets me back to my bond screw, that gets me on my neutral and allows that free flow of electricity and trip the breaker. I got nothing. All I'm going to do is energize that conduit, and everything else that's attached to that conduit is going to be energized as well. All right. So the conduit is more than just protecting the wire and just the convenience of pulling wires through it. That's my ground path. All right. So making sure that those are connected, I can't stress that enough. Without it, if I do have a phase decay fault on the load side, there's no way for me to trip the breaker. Everything's going to be energized. And if somebody touches that and they have another ground path, whether they're barefoot on the concrete or water or touching plumbing pipes, the electricity will flow through them. All right. Bends need to be made smooth, no kinks. Secure 3 feet from the box, 10-foot intervals, Chicago 7. I don't really get into that. I just don't want to see these things loose. I'll go ahead and wiggle them when I come through it. Not acceptable where flexible connection is needed, such as to a motor. Okay, so in other words, if we have to be able to move something, then we have to have something that's flexible for that connection, is what he's saying. Not acceptable to connect to lay in fluorescent lights, because we don't know. And what we're talking about is fluorescent lights in a drop ceiling. We don't know where those are going to land, and so they need to be moved a little bit. So we usually end up putting 6-foot whips on those so we can have access to it. If we go straight to it and we need to take that down, we're not going to be able to move that light fixture to get in there and fix or replace it. So we need to have that flexible conduit there. Coupling, connectors, lock nuts, everything should be tight. Everything should be secured. Again, goes back to losing that ground that we had on there. It's okay to be buried in concrete or earth, provided proper fittings are used and the pipe is protected against corrosion. All right. So this one ended up getting twisted and pulled apart, even though they're still touching. So I still may have my ground path coming back in there. It's still not good enough for me. All right. If those things are loose and they could come apart, that's definitely something we should call out. This one's completely apart. We can see that we have the red wire and the white wire in there. So we have our energized conductor. We have our neutral coming back. But because my conduit is disconnected, if I get a phase decay fault anywhere downstream of this, it just gets energized and I don't have a pathway to come back. All right. BX. All right. BX or armor cable. They have the wires already built into them. So this comes from the manufacturer like this. All right. Those little red heads that you see on there, and let's see if I can, just because I'm having fun drawing on here right now. Those little red head there, they go on the tips of these things. They're designed to protect the wires from being cut from the actual cabling device themselves, all right? The extra wire that's in there, that isn't really a separate ground wire. We kind of tie everything together to give us our grounding system, but there's also not going to be an extra ground wire in there as well. So the armor cable, these are in short whips, 5 feet. We should be able to see that bare metal piece, and I'm talking about this piece way up there. All right. We should be able to see that folded over and folded back so that we know that everything's kind of connected and we have one continuity to everything coming across. Let's see some of the rules. Connectors are straight or 90 degrees, and those are those fasteners that we put on there. The connectors are not concealed, so we can't bury any junction boxes with these. We can fish these wires behind walls. We could do that actually in Chicago now. So we don't have to pull off all the drywall to run new electrical stuff there. We can actually fish the armor cable. But what we can't do is hide those connectors, all right? Sheathing is the ground. No ground wires in the cable. The metal thin strip is not a ground wire, but we want that bended back and visible. Paper wrap around the conductors. That's flame and moisture retardant. That's just to keep them somewhat dry. Anti-short is that red-headed bushing that I talked about, so it doesn't get damaged by the conduit itself. All right. So we can't let it be subject to physical damage. In other words, somebody can't drive over it. It can't be exposed in a garage or someplace where people can step on it or hang on it or whatever. You can fish it in there. If it's run on the underside of the joist, it needs to be secured to each floor joist. If it's going against the wall, 4.5 feet, 12 inches from a junction box. That 12 inches is also the same thing for non-metallic cable. We'll get to that in a little bit. Whatever the thickness is determines how fast I can bend it, but quite frankly, if you bend these things too much, then they're just going to start breaking and coming apart. So BX, what else we got here? It can be unsupported if it's laying loose on top stuff or running behind a wall. Less than, or lengths 2 feet or less at the termination points where flexibility is needed. This is where we were talking about those can lights in drop ceilings or fluorescent lights. Anything where I need to be able to remove something and move it around, that's what it is. And really it's 6 feet is our magic number that I want to be aware of. All right. MC cable is kind of the same thing as armor cable when it comes with it. These, again, open and concealed, direct burial when protected, branch circular signal, similar to the BX or armor cable. Secured every 6 feet. Bending radius is 7 times. Wires are built into it. They do have a plastic wrap on it. Sheathing is not the ground on these. So I don't know if you caught it or not, but there was a separate ground wire in there. And that would need to be attached to whatever boxes that we have. All right. The green ground wire present and must be used. All right. Greenfield. These are basically flexible conduit. All right. Liquid tight, seal tight. You know, even though those have a rubber coating on it outside, it's flexible conduit that comes in there. Now, certain jurisdictions like Chicago, and I was actually, you know, thinking the wrong way on this one for quite a long time, and I do believe it says so in this drawing here, that these can be gone in unlimited lengths, but Greenfield cannot, all right? Quite frankly, if you ever try to pull wires through this stuff, you're never going to get more than 20 feet anyway. But it still falls under the same rules, about 5 feet when you're going to be doing it. But you can run it and fish it under the walls. Not really the most common thing that people are going to be using just because of the size of it, all right? So depending on how you're using it is whether or not you have to run a separate ground wire through this. But for the most part, the Greenfield can be used as your grounding conductor, all right? So not to be used, we're subject to industry within a foot from the box, every 4 feet. Fishing is okay, and it's unsupported when you fish it behind stuff. 6 feet connections. Minimum size is 1/2 inch. This is the unlimited length. Like I said, in Chicago, I don't think that's accurate. Longer than 6 feet, we do need a ground wire installed. Under 6 feet, no ground wire. And most of the time when we're dealing with GFIs, or I'm sorry, when we're dealing with Greenfield, we're going to try and keep those under 6 feet. Any length or any circuit over 20 amps also needs a ground wire. They do have 90-degree angle connectors. Those cannot be concealed. What else? Not permitted on the ground or embedded in concrete. And this is the seal tight version of the liquid tight that comes in here. All right. And seal tight is a trade name where it comes to it. Typically, most of our air conditioning circuits are going to be put in this way. Now realize that the seal tight also comes without that metal conduit. All right. And so what I tend to do is squeeze it. If I can pinch it, then there is no ground wires coming in there. There is no protection of my wires to it. All right. So I definitely need a ground wire coming into it. And that's not acceptable for our outdoor situations. All right. It can be buried if it's marked and listed for this. Not to be used or subject to industry. 1 foot from the box. 4 feet every linear run. Does not need to be secured when flexibility is needed in lengths up to 3 feet. Okay. And this is, this just has to do with the size of the wires, how many amperage it goes on there, if it's okay for a ground or not a ground. And again, it has to do with the amperage and the size of the wires. You know what? You can never go wrong with throwing another ground wire in there anyway. But we want to be as accurate as possible. So knowing that this chart here, 25 amps or more, over 6 feet, it's not okay as a ground. 15 or 20 amps up to 6 feet, you can use it as a ground. So anything over 25 amps, we should have a ground wire going in there. And this again goes towards our feeds for our air conditioning units. And this is what we're looking at here. So here our seal tight actually came loose. I've run into connections for this seal tight or liquid tight where the connections themselves are plastic. And I'm talking about, you know, this nut right there where that thing's plastic. In which case, if it is, then I don't have, even if it is connected, I don't have my, I can't use it as a ground at all, you know, because the plastic will break the ground and go into the air conditioning unit. So I have 2 energized conductors in here, and I do have 1 ground conductor in there. There is not a neutral conductor going through this, but again, if it feeds my air conditioning units, I don't have to have that. All right. Non-metallic cable. I also want you to know the term NM cable. NM stands for non-metallic. NMC stands for non-metallic cable. All right. Also known as Romex. Romex is a trade name. It's the manufacturer's name. But a lot of people do refer to that. I like us to refer to things as being non-metallic cable or NMC. This one would be a 14-2 with ground. All right. So non-metallic cables, they started color coding them. Older systems, I want to say in the 70s, maybe. Oh, I'm sorry. In the early 2000s is when they started color coding these things. And so white would be 14, yellow would be 12, and orange would be 10 when we're dealing with non-metallic cables. And then when they say the first number is going to be the size, the second number will be the number of conductors, and then the third thing is whether or not it has a ground with it or not. So this would be a 14, which is the size, 2 conductors, hot and neutral, and ground. I can actually use this to connect an air conditioning system. All right, it's okay to use the white wire as an energized conductor. We should relabel it as black, so putting tape on it is good, but it can be done. Okay for use on 1 or 2 family dwellings in any height. Suspended ceilings. You know, it's not so much in the city of Chicago and the suburbs around here. We kind of do everything in conduit, and we don't really use non-metallic cable. You can run it underground too. They have UV protection and stuff outside like that, and those are all color coded as well. 12 inches, 4.5 feet, no limit on length. It can be fished. Doesn't have to be supported when you fish it. 6 feet, basically same rules as Greenfield. Type NM is not okay for direct burial. We do have to protect it from physical injury. So basically anything that's below 7 feet that's exposed needs to be in pipe, all right? Or behind drywall. It just can't be out in the open. It's not intended to be used to connect garbage disposals. So those wires under the sinks, because we're going to be going in there, we could bump things on it, we could damage it, and that's why we're not supposed to use it for that. Cannot run perpendicular across basement joist. Needs to be on a linear running board, number 8 or larger. So they have to have something, especially up in attics, and you're going to see this all the time. When you go up in an attic, they don't want you to be able to walk on these wires and squish them, because once we start squishing and damaging that, we're going to be damaging the insulation, and we can start creating a parallel arc when it happens. So parallel on joist is okay. What else? Protected by conduit when passing through floors. Not always happening. So here we can see we come out of our junction box. Within 12 inches of that box, we need to be secured. As long as we don't leave a way for, you know, the wires that are loose. So when they're going through the stud, then they need to be protected with nailing plates. But if they're out in the open like this, then they don't have to. All right. So looking at this chart on here, I know there's something here that says about 1.25 inches. This is all Chicago or all of Illinois. It's Chicago. We use a lot of non-metallic cable in central Illinois. That I know. It's pretty much the collar counties in Chicago is where this comes into play. Thanks, Mark, for bringing that up. But as far as non-metallic cable, just about everything that you're going to use out there or outside the city of Chicago is pretty much going to be NMC. In fact, just to be really clear, other than New York, Chicago, and Los Angeles, everywhere else in the United States of America, and I'm talking about the city itself plus the surrounding burbs and the locale around the city, everywhere else in the United States, they all use non-metallic cable for residential buildings. All right, everything for commercial buildings has to be in conduit, but residential buildings, non-metallic cable is just fine. So what you're going to have down there is just fine. But they still need to be secured. They still need to be supported, you know, whether it's on every floor joist, up against the floor joist, if it runs through a hole. If it's less than 1.25 inches, I have to have nailing plates on it. We still have to protect the wires. We can't just leave them all floppy and loosey, for what it's worth, you know. Here they're showing bundling. And if you notice where we go through the studs, first of all, we got those nailing plates that are up there. So when the drywall guys go there and start putting screws on everything, we don't want them to drive screws into these wires. Now it looks like our nailing plate is missing on a couple of the 12 gauge wires and 14 gauge wires. And I'm talking about this area, like right in here. We definitely want to call that out and get something connected to it. I think same thing on this one. Right in here should also have a nailing plate coming through it. Now the bundling talks about the amount of cables that are allowed to go through that opening that's on there. Now I get it. The wires on the left-hand side are cable and data. I'm all over that, you know. But even though we still want to have those wires protected. However, the yellow wires going up there and the white wires, those are not. All right, those are non-metallic electric. The bundling of the wires, as we're seeing, kind of loose in there, going down the studs. Yeah, that's not so much the problem. It's where they go through the holes is where we're going to be concerned. Because that ends up squeezing everything and then you get a lot of ampacity that comes out of there. All right. This is something that I've never really seen at all, or actually I have. I've seen it a couple times, but it's really rare. I think a lot of people refer to this as like Smurf tube just because it's blue where it comes into it. But it's a plastic, flexible conduit. It's obviously because it's plastic, we can't use it as a ground. We need to have a ground wire running through it as well. But there's going to be some areas where I guess it's okay, you know, but we really don't use that up here in the Chicago area. Knob and tube. There's a lot of insurance companies now that are not, they don't want to insure homes that have knob and tube wiring in it. And it's kind of a big deal when we come through it. So, but identifying it, to me, it's a problem. I let my clients know. I have them check with their insurance companies if we run into it. It's not a mandated defect that we tell people because the wires are tin cladded copper that we normally see. But this stuff is old. You know, this is turn of the century 1900 old. And it's all out in the open. It was not, you know, some of it you'll find in conduit as well, you know, when they merge in newer systems to it. But it's all old. It was all subject to damage and overheating. And we just do things with the plastic insulation so much better. So I would continue on asking my client or recommending that they check with their insurance company and make sure it's there. But nonetheless, I'd like you to know some of the rules, all right, and where they get the names and everything else from, all right? So up here on the left-hand side up there, that's a knob, all right? So the distance on that knob between the floor joist there and then the knob where the wire is, that's actually 1 inch, all right? So when we talk about lifting it up, running off a parallel or on the floor joist or on top of stuff, you know, that's supposed to have a 1 inch gap, all right? So the reason why they make those knobs 1 inch is to maintain that 1 inch gap, right? So when I see stuff like this coming in here, where it's actually resting on the floor joist, even though the knob is holding it 1 inch up top there, I'm not maintaining that 1 inch gap on it as well. So parallel runs, so we're talking about, whoops, this wire here and this wire there. Those parallel runs need to be 3 inches apart. They need to be 3 inches apart. Anytime wires cross over each other, and I'm not necessarily seeing where too much they cross over each other. I guess you can make that argument there. Those need to be 1 inch apart as well. So anytime they go perpendicular, I have to have a 1 inch gap on here. Parallel, 3 inches minimum. And these are all test questions you're probably going to see if you're still taking the state exam. So I want you to memorize those numbers. 3 inches across, 1 inch here, 1 inch to the structure. It needs to stay away. The tubes get their name from where the wires go through the studs. So we're going to have a ceramic tube, and then the wires go through that so they don't get damaged by the wood itself in case it breaks. And again, the knobs are going to be those items there. Splices off of these things, and they are mid-air splices. So when we talk about this one first, a knob and tube splice going to another circuit is going to be going to another knob and tube material. And that splice is actually pretty unique on how they did it. These guys were craftsmen. They were artists. They were, unique in their trade, basically. What they would do is strip the insulation away, exposing the conductor on the first one. So we're talking about the one that goes through here. And that splice up in there. They would strip away that insulation, exposing the conductor. Then they would take the splice and they would wrap the wire around the original conductor, and then they would solder that joint together. All right. Then they would just cover it up with electrical tape. Now, the electrical tape at that point in time was a cloth type material. They didn't have the plastic, shiny electrical tape that we see in today's stores. It was just old and dull and cloth-like that came in there. So if I saw a knob and tube splice go into another knob and tube circuit with cloth jacketed type tape on it, I would be convinced, or I would assume, and I would have a pretty safe assumption, I think, that was done at the time by the original electrician. And even though I'm still calling out the knob and tube as being an issue, that particular thing somebody didn't do anything hokey with. That's just the way it was done at that point in time. But now if I go to the newer stuff down in here, and here they're showing they put a non-metallic cable and they spliced into that knob and tube wiring. Now I have new wires that come in here, and now I'm trying to splice into the old knob and tube. Chances are that's not going to be soldered together. Chances are it's going to be using the newer electrical tape. And quite frankly, our knowledge has grown since this electrical system was installed. So we can tap off to it. They did make ways to do it. But all these taps have to be in a junction box, all right? We don't do mid-air splices in modern electric with non-metallic cable. We never did. So if I see any sort of NMC or NM cable that goes to a knob and tube, that in itself is going to end up being a problem. So we would want to photograph and document that. All right, needs protection, floor level to 7 feet. That actually goes the same for any NMC. No insulation. That's something that I forgot to mention earlier. These wires have to be out in the open, all right? So if they're running inside walls, I can't fill those walls up with insulation. If they're up in the attic, I can't cover them with insulation, all right? They do need to have clearances, again, 3 inches between themselves or 1 inch to a structure or part of the surface itself, all right? Parallel to each other and intersecting. Yeah, when they go over each other, it's 1 inch. When they go parallel, it's 3 inches. All right, you could stack 2 knobs up when it comes to it. So here's our knob, there's our 1 inch. And what they would do, and I'm talking about this one up here, what they would end up doing if they needed another wire that goes on top of it, they would actually install another knob directly on top of that knob, which would also be another inch up above. All right. Now they took some of these old knobbing tubes and they wanted to get some more electricity coming in here. So now we have a junction box. That's the right way to do it. All right. But if you look carefully and you see a little, I think it's a wire coming out of there, out of that junction box at the very top. It looks like we ran a ground wire and the neutral wire, and basically they just brought blank wires coming out of there. And I'm hoping we'll all realize, no, you can't do that. All right. Oh, they did. Here's a close-up of it. And this is the area that I was talking about right here. So that opening is 3 inches apart, and that's where they need to be. This is what the old splices end up looking like. Now, when you come off the splice right away, you don't, obviously you can't get to that 3 inches right away. And what they're really talking about is between the hot and the neutral. All right. So just because it's 2 neutrals or 2 hots, they can actually be close together like this. That's not hurting anything. What we don't want to do is allow for something to fall over the top of it. Me personally, I think it should be further apart, but 3 inches is what the rule was. All right. Old splice like that, this means that was done a long, long time ago. So here's a nice picture of our tubes coming through here. And our knobs coming on there. They're not covered with insulation. You can see they did put insulation in the attic, but they left our wires free. Here we're going with either armored cable or greenfield. Once we do something like this, we have to be in a box. And that's about enough on the knob and tube. All right, square D breakers. And more so, we're going back into the panels a little bit. One of the usual suspects that we find doing home inspections are double taps. I want to say just about everyone that we see is going to have 2 wires under a lug. All right. And sometimes it's okay. And sometimes it's not okay. All right. So I'm pretty sure there's other breakers out there that are designed to carry multiple wires under one screw. But right now, the only ones that I ever see are the square D breakers. All right. And I'm going to go to the next slide first. And this is the side view of the square D. So these have 2 plates on it. And then the screw actually pushes down on that plate. So this particular breaker, again, this is the square D one. This particular breaker is designed to carry 2 wires, all right? But it's only designed to carry 1 wire on each side of that screw. If we go back to the other slide, we could see on this one, they put both wires on one side of the screw. That it is not designed to do, all right? So you could put 1 on each side. It is designed to hold that, but not 1 or not 2 on the same side. And again, square D is the only one I'm aware of that does this, all right? Now this code here is actually changing. In Canada, they had it for a long time that switches and outlets all needed to be either 3 or 5 feet away from the tubs, all right? In the United States, they just couldn't be in the tub, all right? So here the question was, an electrical switch must be at least 3 feet away from the bathtub and shower. Originally, that was false. 406.8 says it can't be in the shower space, all right? But this is changing, and this is going to be adopted by more and more municipalities as time goes on, and they are going to be pushing that 3-foot rule to keep it away from the tub. I honestly don't know how they're going to get around some of these things unless, you know, they separate. Obviously, it's got to go. Tub is always going to have to be in the back wall somewhere. Then you're going to have the toilet and the sink in order to get that space. But it is changing, all right? So here in this diagram, the outlet is actually inside of it, and that cannot be in the plane. Once you cross the plane, it's bad, all right? This is on the outside, you know, and again, it just can't be inside the plane. Anything near our water sources should be GFIs, and I didn't really talk about that all that much. GFIs are easy to install. They're cheap. You know, a handyman can really do it. It's light electric where it comes to it. But anything outside nowadays, anything in a garage, anything in an unfinished basement, kitchens, bathrooms, those items should all be GFI protected. All right, plain and simple. This isn't a, I haven't seen Joe in a while. This is a great guy. I'm not even sure if he's still a home inspector. But he came through our program a long time ago, and we were looking at a foreclosed house, and somebody decided to put a shower in the bathroom, and we got an outlet obviously inside the shower. That's kind of a no-brainer, all right? This one we saw earlier. Anytime I overload the neutrals, and it is possible to overload neutrals, if I'm sharing that neutral and they're both on the same phase, I can easily run too much electricity than what it's designed to carry. And also, if those wires are loose, they will create a series arc, and that arc will cause the insulation to melt and burn, you know, just like this. So there's more than one reason, I guess, is where I'm going. All right, something unusual that we may see is locks on circuit breakers. A lot of municipalities are requiring fire alarm, sprinkler systems, smoke alarm systems, all of them to be in the locked on position. All right. Now, you're probably thinking, well, if it's locked in the on position and that thing won't let it move, because every time I see a trip breaker, it's actually moved to the middle position. And I can relate to that. I can understand it. But rest assured, this breaker will still trip should there be a need for it to trip. So if I have an overload fault, a direct short, or some sort of ground fault and I'm bonded properly, that breaker will trip. So having locks on them is a good thing. And even, you know, they have lockout tagout kits. And now it shouldn't be locked in the off position. If it is, chances are good there might be somebody working on a system somewhere, and he locked it off so that nobody can turn it on by accident. I would obviously investigate that. If somebody worked on something such as the air conditioner system, they locked it out, they forgot about it, and they're not there anymore, then when your client goes to use the air conditioning system, it's not going to operate because it's locked in the off position. But I think that's rare, and I've never seen anything like that. This is using disconnects or anything that had a separate fuse in it. You know, if they're going to go ahead and run copper pipes, obviously that's not going to work as a fuse, and that's going to create its own problems itself. Overfusing. This is the math that comes with it, and I'd like you to go back to that chart that we wrote earlier. And that chart is pretty much going to be our rule of thumb, all right? So certain appliances, not all appliances, but certain appliances, we can overfuse. And it's still safe, all right? Now, this is a rule of thumb, all right? What we don't want to do is rely on this to be steadfast rule that comes into play. But let's take the central air conditioning systems. And for us in residential home inspections, where we're going to see overfusing is typically going to be the central air conditioning system, well pumps, and electric radiant baseboard heat. Well pumps, we're not going to see the data plate, so we're just not going to know what size wire and what size breaker it calls for. Electric radiant heat, not always are you going to see that either. All right, you have to start taking things apart and dismantling them. And we really don't do that to see it. But air conditioning systems, on the other hand, you can see those, all right? And we can take a picture of that data plate that's on there. So the shortcut, if we remember, we had our amperage written first, and then we had our copper conductors and our aluminum conductors. So 15 amps was a 14 gauge, 12 amps, 15 amps was a 14 gauge, 20 amps was a 12 gauge, 30 amps was a 10 gauge, 8 gauge or 50 amps went all the way up to an 8 gauge. So the rule of thumb for us is whatever wire we have there, and that's only specific to those dedicated circuits, all right? Once I start mixing circuits, I can't do this any longer. It's only when it's dedicated. And it's pretty much what we want to do is avoid nuisance trips. We know that when an appliance starts up, there's going to be a heavy draw, and we want to let that draw happen, and then everything's going to back down where it's going to be normal, all right? We can't guarantee that when we have multiple items connected to the same circuit. So this is only for dedicated things. So what we're saying here, the best rule of thumb is you go to the next size larger wire, and whatever breaker you could put on that wire is pretty much what you could have this wire protected at. So if I had a number 10 copper wire, which is typically going to be on a 30 amp breaker, I would take the next size larger wire, which is a number 8, and that chart that I wrote up before, that number 8 says I can go all the way up to a 50 amp breaker. So in this situation, is it okay? The answer is yes. All right, you could have a number 10 wire on a 50 amp breaker. However, this rule of thumb, like I said, it's pretty much only going to be for well pumps, or it's going to be for electric radiant heat, and there's no way for us to verify that. With air conditioning units, and we could see the data plate, we should be able to tell what size wire that calls for and what size breaker should be on there, all right? So here they allow us to be 175% over, but we can't exceed 225%, all right? This term here, and this is our second to last slide, we'll throw one more up there and we're going to end this. This one here, I refer to this as top loading, all right? So we got a 100 amp breaker, and so the red striped wire has a single 100 amp breaker. The black wire has a 100 amp breaker that comes in there. They're tied together, all right? So even though we have two wires and each one is on 100 amp breakers, again, we do not add these up. This is still a 100 amp service that comes in there. Those breakers will allow up to 100 amps to flow, all right? Whether they're flowing at 120 volts or 240 volts, doesn't necessarily matter. It's going to allow 100 amps to flow. The problem now comes in with that black and white wire that's tied in off the top of this. So those wires also are only designed to carry 100 amps. But now, if those wires, we don't know what they're hooked up to, but let's say they're hooked up to something that's going to allow 50 amps to flow. Now I'm going to be able to allow up to 150 amps to flow down those wires that are only designed to carry 100 amps. Those wires should be after the main breaker and not before the main breaker. This main breaker is not going to be able to sense how much electricity is flowing before it. It only knows what's flowing through it. So if those wires are top loaded like this, we're not going to have the luxury of having that breaker protected, and we could overheat our wires. All right. Last thing I want to chat on is can lights. And then we'll wrap it up, and I hope this all helped you a little bit. So if you do have any questions on anything I chatted about, now's a good time to start typing them in there so I could address them. All right. So there's two different types of can lights. The one we're looking at here is what they call non-IC rated can lights. So IC stands for insulation contact. That means if it's non-IC, that means that insulation cannot touch this can light. Typically, they're painted white. Not always, but typically they're painted white. If we're lucky and we see them, then you could see the old sticker right on there that says, hey, you have to have 2 inches or 3 inches of space around this can light to make it. Now they do make boots that go ahead and keep the can lights, and I've seen people put boxes around it to keep the insulation from getting around it. But these are pretty drafty as well. And if you have these can lights up in an attic or an unconditioned space, you're going to have a tremendous amount of heat loss coming up through there, because this opening down here at the bottom, I couldn't get down there, sorry. That opening down there at the bottom, that's clearing through. You'll actually see light shining through there. Same thing where this pipe comes through. So once those bulbs start getting hot, heat just goes up into the attic. And once we start heating our attic, and then we're asking for a lot of other problems such as ice damming, moisture, everything else that's going up in there. Not to mention it can't dissipate the heat of these things, so we don't want the insulation touching it, all right? IC rated can lights are typically going to be silver or unpainted. That doesn't mean that they all are. They're, it is what it is. And not always can you tell the difference without seeing a label that's on there, all right? If you put a can light like this in between the first floor and the second floor, so we go in the first floor ceiling, and you don't have any insulation between the first and second floor, that's what they're designed for. That's fine. All right, but once we start putting them in attics or ceilings where the attic above it is an unconditioned space, now we're asking for trouble. And this is not a good idea. I don't know. So white is typically going to be non-IC. Silver is going to be typically IC rated. And I think that's all I got for you. There is more things with electricity we could talk about, but I am actually losing my voice right now, and I'm just going to call it a wrap. And then I think I'll get some of the interior stuff on another day. So for those of you that are here, I want to thank you. And that is that.